we go. Okay. So last time we were talking about situation with our independent sample t-test where if we have unequal sample sizes and some of the issues that that can create for the calculation of our test statistic. Did people go through, read that kind of long email that I sent out, sort of trying to go through, wrap up things and kind of explain some of those concepts? Did that help solidify things at all? People read that? Okay, so go through, take a look, just trying to sort of make sure that we understand kind of what happens in terms of this weighting and sort of thinking about precision and sample sizes and things along these lines. So we talked about the fact that, remember, and this kind of relates to, I think, the first problem on problem set 3, our entire statistical sort of approach is based on the assumption that we know the distribution of something, right? So if I say my t statistic is equal to x minus mu over sort of my standard error, right? And that's the, well, this. We're talking about independent sample test. X1 over X2 is equal to the standard error. Well, we'll just use this so that it matches up with what we've got here. Standard error, the difference in means, right? We assume that we know for a given degree of freedom, we know that this test statistic has this distribution so long as population 1 minus population 2 equals 0, right? Assuming the null hypothesis. Assuming this is true, we know that the difference between any two samples that we go through and pull from this, we're going to have a t distribution with the degrees of freedom that follows this this distribution. And that's how we can go through and start assigning probability functions to probability statements to this to say, yes, assuming that the null is true, these data would be likely, unlikely, assuming that all my auxiliary stuff is intact, right? The problem is where we start to lose confidence is if we create a test statistic that doesn't follow this distribution. If we start to violate things, now all of a sudden we've got a test statistic that doesn't follow the distribution we're using to put that attach that probability to, and now all of a sudden we start to lose confidence in stuff, right? So an informal assumption of our independent sample t-test is we got reasonably similar sizes. In experimental work, we can often do this, but a lot of times with, if we're looking at naturalistic stuff, right? Pre-existing groups, we can assign someone to certain types of groups. Sometimes we're just unbalanced in terms of the numbers of people who we can recruit. This starts to create complications that we then need to take account for, right? And so this is where this pooled variance estimate is helpful, because what it does is it makes sure that the sample with the lower number of people, any individual in there doesn't have an undue influence on the variance, and sort of giving greater weight to, again, we're assuming equal variances in the respective population, giving greater weight to the estimate that's coming from the sample with the greater number of people, okay? This kind of ring bells, sort of pulling all together in terms of sampling distributions and how everything is based on our assumption that we know the distribution of this statistic, assuming that the null is true. Okay, so again, otherwise we've got paranormal distributions. We're very scared and spooked, and it throws off all sort of our conclusions. Okay, so thing we're going to jump in, cover before we jump into the actual example here, thinking about measures of effect size for our independent sample t-test. Raw difference. This is, again, a really nice metric if we're using something that has some sort of meaningful units, right? If I'm talking about dollars, weight in pounds, number of drinks that I have per sort of whatever, reaction times, maybe if that's something that impacts or sort of is something that's interpretable, sort of number of kids, things along these lines. Raw difference can often be a nice metric because it's something that I can just look at and say, hey, yeah, I know what this is, and that's a lot or a little. So I think an underutilized metric, but something that we can go through and take a look at. we also have another version of Cohen's d. Okay, Cohen's d here is just our mean 1 minus mean 2 over our standard deviation. Okay, but things get a little bit more complicated in our independent sample t-test because all of a sudden now in our single sample t, we just had one sample standard deviation, right? It was just from the one sample that we had. Now all of a sudden we got two samples. So the question becomes, what standard deviation do I use? What's my standardizer? Okay. And so here we've got a couple of different options that now we have to think about what makes the most sense given the research question that I'm asking. Simple approach, if we have, say, a control or a reference group, some group that's just kind of, hey, this is sort of your everyday ordinary stuff, a good comparison group, what we can create is sometimes what you see called or referred to as Glass's delta, okay? Numerator is the same. You're just taking the difference between your two groups, but what you're doing is you're using the standard deviation of your control group as your standardizer, okay? This is nice because then you can say, yeah, interpret your effect size as saying, my experimental group scored 0.8 of a standard deviation above sort of my control group based on variability that we would expect in the general population, right? If your control group is just the general population, sort of everybody, and we kind of know what this measure looks like and variability looks like in the general population, then we can just say, yep, sort of half a standard deviation relative to what we would expect in the general population. It's kind of a nice basis for understanding stuff, right? So what I can do is just go through and pull the standard deviation from that control group or reference group or whatever it is, and just use that as my standardizer, okay? Because remember, our means-based effect sizes are always, they're just like z-scores. We're just talking about things in terms of standard deviation units, right? And for us, as statisticians, we understand what a standard deviation means, assuming sort of within a normal distribution. So we can say, yeah, that's a lot, that's a little, so on and so forth, okay? Questions about Glass's delta? Okay, sometimes we don't have a good comparison group. Sometimes we have two groups that are on equal footing or two experimental conditions that are sort of equally sort of new to us, right? There's no real reason why one group should be the reference group over the other. And in that case, what we can do is we can change our standardizer and we can just use our pooled variant, the square root of our pooled variance estimate, okay? This is gonna be our, say, our pooled standard deviation, okay? Now, the thing to, and this is just kind of the weighted average, right? This is basically this is just the same variance estimate or measure of variability that's going into our t-test, right? If we go back, right? So this pooled variance, sort of this thing that we're using to calculate our standard error, we just take the square root of that pooled variance estimate and use that as my standard deviation here, okay? And this is just kind of like the average variability across there, right? And so again, this is nice. We can say group one exceeded group two by about 0.3 of a standard deviation, sort of relative to variability across the groups or something along those lines, okay? So a kind of a nice interpretive way. This is often kind of our default when we're thinking about this, right? Because it just kind of splits the difference. Questions about hedge? And so this pooled variance estimate. Cohen's d, this is old school Cohen stuff, right? And Cohen just said, yeah, you take the difference and then take it over the standard deviation, right? And if you ask Cohen back, which standard deviation do I use? Cohen will probably say it doesn't matter, right? Because we're assuming that the variances are equal, so who the hell knows? Pick one, right? Theoretically, it doesn't matter. But from a practical standpoint, it does matter, right? Because one of those variances is going to be larger than the other. And in terms of calculating your effect size, which one are you going to be tempted to use? Bigger one or the smaller one? Smaller one, because it's going to make my effect size bigger, right? So we're kind of an ambiguous, in theory, it doesn't matter, but practically it does. And so we've got some different options. And so you'll often see, and you'll see this in SPSS, this referred to as Cohen's d. It's fine, there's just no standardization. Just know what the standardizer is, and then sort of just make sure you're communicating what's going on there, okay? Last thing that we know is that as we're going through mess around with this. If we are looking at measuring our effect sizes and we're working with very small samples, what we know is that with very small samples, we're almost always going to overestimate our effect sizes, right? If we take a look at here, this graph, where we look at our effect size along with our degrees of freedom, see very, very large effect sizes, but as we start to get more and more people in our sample, we see that start to asymptotically hit kind of the more correct nope, scratch that. That's not what that's looking at. Never mind. Forget that piece of things. We know that in small samples, we're going to overestimate our effects systematically. Okay. And if we think back to some of those old school experimental types of studies where it wasn't uncommon to have, like, say, 7 or 8 people in an experimental group, right? Like, I've got a published study with cell sizes of like 10 or something along those lines, right? Part of the reason we can understand in terms of some of that replication issue is those small studies probably wildly overestimated the effects just because there's not sort of that many people in there. And so what we have for small samples is a correction, okay? And if we take a look at this correction, what we do is we go through and we just calculate our Hedges G like we would normally calculate, but then we go through and multiply it by this correction factor, right? And this is kind of complicated. 1 minus 3 over 4 times N1 plus N2 minus 2 minus 1, sort of plug stuff into there, okay? And Basha, as my sample size starts to get larger and larger and larger, what happens to this number here, like the whole thing? Well, if we increase the denominator, it gets smaller, right? And if I subtract 1 minus a smaller and smaller number, I get a bigger and bigger number, right? And so then for large samples, if I multiply my effect size by this, there's not much of an adjustment, right? But what happens if I have small numbers? Let's say I have samples of 10 and 10 in there. What happens to this number here? It's bigger. And now I'm taking 1 minus, say, 0.5, and now I'm multiplying my effect size by 0.5, right? And so what we get is an adaptive correction factor. As my samples get bigger and bigger and bigger, the correction gets smaller and smaller and smaller. And so this is what we're looking at, sort of looking at the impact of that correction factor as my degrees of freedom get bigger and bigger. It starts to sort of have a less of an impact on things, okay? So when you're working with samples that are pretty small, what we can start doing is saying, should we assign a correction factor to this? And in SPSS, when you look at the different effect sizes that it'll give you, it'll talk about, I think it gives this as Hedges G, and this is just inclusion of a correction for the small sample bias. Yeah.
Quick clarification question. So we have the unbiased G, we need to first calculate Hedges G and then multiply.
Yeah. Okay. Yeah, that's all it is. You're calculating this, and then you're just saying, hey, I'm going to correct this if I'm worried about small sample bias.
Okay, cool.
Yeah. Yeah. Just that.
Hedges G already have a small correction for sample size?
The pooled variance is going to be, pooled variance isn't necessarily tied to small sample, right? Because I could have 100 in one group and 500 in the other group. I've still got a discrepancy in my sample sizes, and so it's going to weight that out. So this isn't necessarily specific to small samples, although oftentimes the unbalance does involve small samples, but it doesn't have to. Okay. And so this is just saying, if I'm working with pretty small samples, then I should probably go through and have this. And so you can see here the impact. So we hit diminishing returns, again, thinking about sample sizes of 30-ish, 25, 30-ish types of things. If you're worried about whether or not, because sort of what everybody wants to know, like, how many people do I have before I use this? Who the hell knows? I don't know. It's sort of up to you, right? That's a decision that you have to make and justify. You can always just go through and sort of calculate bias and unbiased and sort of look if there's a big difference. This is something I should take a look at. If there's not, I'm not going to worry about it, right? This is going to be your more conservative estimate, but as your sample size starts to get bigger and bigger, the difference is going to start to become more trivial. So just going through and think, now if you've got obviously small samples, this is probably what you should be looking at, but otherwise you can just kind of sort of, this is where the applied piece comes in. This is up to you to sort of say, this is what I use as my standardizer, this is why, and sort of take things from there. Yeah.
I'm trying to contextualize the equation, but with the N1 plus N2 minus 2, is that the minus 2 for degrees of freedom then?
Yeah.
Okay.
Yeah. Yeah, it's such a good call. Yeah, this is just basically your degrees of freedom. I mean, this is the formal thing, like N1 plus N2 minus 2. You could have done sort of N1 minus 1 plus N2 minus 1, right? So yeah, there's some redundancy in that equation, but just make sure that you're calculating correctly. And what I'm gonna have you do for this, not this, the following assignment, I'm gonna have you put together an Excel spreadsheet that has all this stuff in it. So starts to make it easier. What's nice now that SPSS will do this for you, you can just like click the thing and it'll just pop it up. So long as you're 100% sure you know what standardizer is being used. But there's going to be come times, I guarantee, that you'll be looking through a paper and have wanted them to calculate an effect size for you, but they didn't. You can do it by hand, but also if you have a handy dandy Excel calculator you developed here, just pop in stuff, it'll spit out your effect size. It ends up being pretty handy. Okay. Questions about sort of our usage here? Yes.
Is it expected that when you're replicating studies that the effect size will go down just because estimating in general? I don't know if that's what you were saying at first.
Okay, repeat that to me, Basha.
So like if we're replicating a study,
Uh-huh.
and at first the effect size was really large, and
Uh-huh.
the second time it's really small.
Uh-huh.
I know Greenwald was saying that's pretty common, but I
Yeah.
don't understand why.
Okay, so again, I'm just going to repeat you just to
Okay,
try and get
sorry.
no. It's to try and get sort of these questions on the video. So the question is, so like I'm going through and I've got a study that has an effect size, and then I want to go through and replicate it, and I run my study, and then my effect size is much smaller than the one that was reported in the study. Kind of what's going on with that, right? A lot of different things. Okay. One thing we know, as we talked about before, if let's say I've got a study and the population effect is actually 0.3, something in the smallest range, right? But in order to get the power to reliably detect an effect of 0.3, I need to have pretty big sample sizes, oftentimes bigger sample sizes than people are using. And so if people are getting studies that aren't sort of getting that threshold, that 0.05, and they kind of falling around here, they're not getting published, so no one knows about them. But then someone, the person who's running the study that you pulled, it got published, and it says it's got an effect size of 0.9, right? Well, yeah, but they just happened to catch something on the far end of that distribution, just happened to catch a sample that had sort of wildly overestimated the actual population effect. But they were using the same number of people as these folks were. They got more reasonable estimates, didn't find statistical significance and couldn't publish. This person just kind of got lucky in that they got a statistically significant effect. It just wildly overestimated with the actual population value. So there's probably going to be, and we talked about just the way our publication system is set up and sort of our current replication crisis, this probably accounts for quite a big deal of it, right? So they probably just wildly overestimated. So even when you're going through, unless you have like meta-analyses and you're like, okay, across multiple studies, this is kind of giving me sort of an idea of where ballpark this should be. If I'm basing it off of one study, it's better than nothing, but I'm really sort of, it's questionable sort of what that effect, unless it's like a study with like a really large sample, then you maybe have better idea or confidence in that. Other thing too, we'll talk about this in the next lecture when we're talking about confidence intervals on effect size. Confidence intervals on effect size get kind of tricky because what ends up happening, just kind of a preview, instead of a central t-distribution where everything's nice and symmetrical, we're working with a non-central t-distribution for reasons we'll get into. And what ends up happening is the confidence intervals around effect sizes often end up being quite large, uncomfortably large. We don't like effect size, or we don't like confidence bounds to begin with, because it says, hey, maybe your effect isn't as big as it is, or maybe it's massive, who knows? When we start calculating confidence intervals on effect sizes, that interval estimate gets really big. And so if we continue to interpret that confidence bound as based on the data values that are supported by these data, here's my best guess, but anything from here to here is reasonable given the data that I've collected. Another reason that that probably starts to go through, and we see probably are likely to see wild, pretty big changes in the estimate of effect, especially when we start using different methods and pulling from different populations and using different measures and using different sample sizes. All that stuff kind of plays into this. That help out and sort of, okay, cool. Other questions about our effect sizes for our. Okay, so you've got some, you'll have options available to you. What you need to do is think about the question being asked, what are we doing? And then think about, okay, which one of these is the best fit for what I'm trying to accomplish? All right. Last thing, what we can do, and this is really handy. We can go through, assuming that someone's published sufficient information, we can start calculating estimates of effect size based on T statistics. And this is really slick, right? Our best journals would generally sort of require you to have estimates of effect size or tell you why you didn't, but it's still pretty hit or miss, particularly in clinical. If someone's reported T statistics, you can go work backwards and just with those T's, go through and get an estimate for D. Or maybe they're not giving you the T statistic, but they gave you means and standard deviations. You blow those means and standard deviations in, get the T statistic, and then work backwards from there, okay? So a lot of this is end up sort of piecing parts together to get kind of a Frankenstein monster of some estimate of your effect size. Hopefully people are just providing those out there for you. But this is a way we can go through and reverse engineer and get that information, even if it's not provided in a paper, okay? Now, if I do have access, if you're doing your own research, use that, just calculate them directly. These are approximations, right? Don't screw around with that. Do this, right? But if you're having to hijack information from a paper to go through and calculate stuff, these are our formula that you can use to reverse engineer stuff. Okay. All right. So, example. So kind of work through. Oh yeah.
Right. Back to the other slide.
Yeah.
So in the corner of this film, like the way they say to fully use those, like you're just.
Yeah.
Like in orange, we're using pounds that's small,
Yeah. So in the process, sort of, do you want us to do what I want you to describe small, medium, large? Yeah, but within context, right? So like I am fully confident that you can determine sort of where things fall and sort of attach those labels. So that actually doesn't provide me with any sort of real meaning on whether or not you understand things. Now things are really large, are you getting an effect size of 1.2, you like sort of really large effect, or if something's 0.3, you say sort of small, or if something fell on like something and you get an effect size of 0.05, right? You say like fall below standards for conventional standards for small effect. So yeah, I mean, these are nice kind of anchors in terms of just general communication, but there's nothing about this that's hard or fast or necessarily relays anything sort of directly about the importance of an effect, okay? I've got you, you're reading like when small effects are impressive, so that paper. Have you reading that one? Is that next semester? When small effects are impressive. Is that on there? Okay, that goes into some interesting arguments, right? The big effect size isn't the end all be all, right? A lot of the stuff that we're looking for is going to be small, and sometimes those small effects, if we can tease them out, are pretty impressive. Okay, again, I've sort of talked about some of Sean's stuff, some of that priming stuff. If you get anything at all, that's pretty impressive, right? The fact that I gave this manipulation and found some sort of because if I look at it, I'm like, should say that's ridiculous. There's no way that's going to impact behavior. But if it does, that can still be kind of impressive. And sort of talking about sort of different situations where those small effects can still be pretty impressive, which is why we don't, this isn't a hard and fast rule. Cohen didn't send these down from Sinai on stone tablets, right? Like this is general sort of guidelines for, this is kind of what you might think about in terms of things. But unfortunately, people often use it less thoughtful and say, you've got an effect of 0.79. Back, well, that's not large because 0.8 is large. Ridiculous, right? So just use these flexibly like any other guideline. Other questions? All right, cool. All right, so our independent sample t-tests here. Say researchers are interested in school performance in students having viewed Sesame Street children, those who had not. Scholastic performance in 10 high school students having viewed Sesame Street in childhood were compared with 10 students who had not. Students having watched the program had a mean grade of 93, variance of 22.2, while those with no exposure had a mean grade of 85, variance 17.8. Okay, so we've got a situation, we've got equal sample sizes, but unequal variances by at least a little bit, probably not anything we're too worried about. But what we want to do here is walk through same thing we've done before, null hypotheses, null and alternate in symbols, 95% confidence interval for the point estimate of, that's not interpersonal difficulty, that's grade in the sample, absolute difference in the magnitude, right? We're talking about effect sizes, conducting a test, S value, Bayes factor, and then pulling this all together for a conclusion. Okay. So just to go through and kind of sort of my handwork on this, right? Right here, this is what I often do, is just nice for me to just kind of write down sort of the descriptives, pull those from the problem. So we've got no Sesame Street. Sample sizes are the same. We've got mean for this group, mean for that group. And then we've got my two variances. Just a nice way to go through and sort of tie this together, right? Okay. So what's the first thing I need to do then if I'm going to go through and run sort of this confidence interval? What do I need if I'm going to do any type of statistical test? What do you think, Katie?
I think you need to first state your null hypothesis, and you need to know the mean, the standard deviation.
Oh, okay. What did you say there?
Standard error.
Kind of standard error. Standard error is always the answer to most anything. It's if you had to just like randomly choose an answer, standard error is probably right. It's a good guess. It's like D on a multiple choice test. I don't know all of these, I guess, right? So here what we're going to do, but remember we've got unequal variances. So what we're going to do is we're going to go through and first calculate our pooled variance. So here my pooled variance, remember, is my first sample minus 1 times my variance, second sample size minus 1 times the variance over my degrees of freedom here. Okay, so I've got 10 minus 1 times my first variance plus 10 minus 1 second variance here all over my degrees of freedom gives me a pooled variance of 20. Okay. You see how we just kind of plugged that into the formula and got my pooled variance across these two. Okay, this is a sample I pulled out of a textbook, so it gives us nice round numbers, which is pretty slick. That won't always happen, but all right. So I got my pooled variance. So now what do I need to calculate, Katie? Standard error, right? All right. So my standard error is just the square root of my pooled variance over my sample size 1, pooled variance over sample size 2. Here what we're doing, we're just plugging in my pooled variance, right? So if I'm doing this correctly, that variance estimate is going to be the same across both of these. So I've got 20 divided by 10, 20 divided by 10, take the square root of that, gives me a standard error of 2. So now I can take that standard error and now calculate a confidence interval around my difference in grades across my group. So I've got 93 minus 85, my two means, plus or minus 2.101 times my standard error is 2. Matt, where did I get 2.101? That's the critical value, right? My critical value, right? So I either went through on my critical T, calculator or whatever, punch that in, or look at my table. I've got how many degrees of freedom do I have in this test, Basha?
Wait, oh. Wait. But it would be n minus 2, right? Because we're going to-
Yeah.
Then, uh,
18 degrees of freedom. Nope, you got it. Right. So if I go through and I take a look at my t-test table, look at 18, sort of go down through 0.05, two tails, what I'm going to get is a critical value for a t-test, a t-distribution with 18 degrees of freedom. Okay. So I've got my difference, plus or minus my critical value, multiplied by my standard error, gives me a value, a lower bound estimate of 3.8 and an upper bound of 12.2. Okay. Teresa, can you give me an interpretation of that interval?
Is basically saying that compatible values for the grade, the mean grade,
Uh-huh.
or compatible values fall within.
Exactly. Perfect. Probably what I wanted is because again, sort of to say this, because this is an interval estimate, I might say something along the lines like estimates of the population difference across these two groups, anything ranging from about 3.8 to 12.2 supported by these data, right? What's our best guess?
Our best guess is going to be
The mean difference, right? So that's still 83. So 8 points is going to be my best guess. But these data here will support anything from 3.8 to about 12.2. There's that.
So for, so on this one, since they have different means that are very different.
Yep. Well, you could, yeah. With this one, because our independent sample test is always the difference between the two. With our single sample test, sometimes you see that SPSS calculates it around the difference between my reference value and my test and my sample statistic. You could also just calculate it around sort of my sample value. 6 one way, half a dozen the other. Sort of depends on however you want to go through and calculate it, right? But for this, because the question is I want to get an estimate of the difference between mean value in population 1 and population 2. My best guess is 8, but these data are consistent with anything ranging from just a little under 4 to a little over 12. Yeah, Emily. Yeah, that's a good question. Look at that, you jumping like 2 lectures ahead. Then we can start to get into ANOVA models,
Okay, that's
right? Okay. And then if we've got more groups, that's when we're going to go through. But even when we run those ANOVA models, at the end of the day, all our ANOVA model is just saying that, yeah, these groups are different somehow. We then are back into sort of pairwise tests to go through and try and make some sense of that. So, yeah.
I thought I wanted to make sure.
Yeah, Teresa.
Is there a way, and I don't think that it's easy to interpret with it's the simulation this or overall, but is there a way that we could interpret?
Is there a way to interpret the pooled variance meaningfully? I would just say that it just is what it is. It's kind of sort of the weighted variance of the two samples. And again, assuming we don't have a violation of homogeneity of variance, then it's sort of trivial anyway, because we're assuming that the populations from which these samples are drawn share an equal variance. So this is just kind of weighting it out to give us a sort of recognize that we have greater precision in one group versus the other. But yeah, kind of average variance, or so which we'll get into with the paired sample, the pooled sample, it just kind of sort of saying the combined variance, or sort of the if you start getting into sort of the weighted variance of both, then that starts to probably get into a little more wonky that anybody outside of sort of stat nerds will probably appreciate. So you can just sort of talk about sort of the combined variance or something along those lines. Other questions? Okay. Elizabeth. So the next thing, we're going to jump in and do the t-test. Do we even need to do the t-test at this point? Based on the information we have? Okay, we can, sort of depending on sort of what scratches my itch and what I like to see in terms of tests. is there any question in terms of what decision I'm going to make? Reject, fail to reject the null based on the information that I've collected already. Well, I mean, I'm going to have you go through and calculate a whole bunch of other stuff. But if all I'm interested in saying, do I have evidence for differences in these groups? Do I have enough information to make that conclusion, or do I need to sort of do some other special magical stuff?
Like I said, we have information, but I feel like the more information, better to do.
What about, so Emily, I saw you sort of nodding your head back there. What can I make a determination on differences here? Yeah, how do I do that?
Because is there any difference between have a difference of at least 3.8 points?
Yeah. And so what's not in that interval? 0, right? And so that's the thing. If I'm looking at this interval estimate, my null hypothesis is that the difference between these two groups are going to be 0. Essentially that these groups are equal, right? But I can just look at that interval and I know that 0 is not in there. So is it possible that these populations have 0 difference? Sure. Is it likely given sort of is that reasonable given the estimate that I got? No, right? I don't have a very precise estimate, but I already know that my p-value is going to be less than 0.05 because 0 is not in there. Right? So we can go through and we will do that test. But again, the only thing special and unique we get out of that test is it's using all the same information. It's not additional evidence. It's not sort of more stuff. It's just repackaging this to go through and provide that p-value. But really, that interval estimate gives us all the stuff that we already know about sort of this, what our traditional approach will sort of want us to do to make a yes/no decision. See where that's coming from there?
And I guess the way I took it, I'm confusing myself a little bit more in that I know that we're saying they're the same, so there's 0 difference.
Uh-huh.
I took that very literally as like you would want to see 0 in between as a value in the constant interval range. But I feel like that's not the case.
Yep. So the opposite. So, I mean, what we want in our life is rarely what we get. And so life is a constant struggle with disappointment, right? But what we can go through, we say the null hypothesis. If we're saying that, yeah, really academic performance in sort of individuals who have been exposed to Sesame Street and those who haven't, there's no difference. They're the exact same, right? If that were true, sort of we would expect 0 to be at least sort of a possible value in there. We don't expect the actual difference needs to be specifically 0. It's always going to be something, but these data are saying, at least from our perspective, sort of our approach, we're saying that assuming that there is no difference in average grade of individuals who've been exposed to Sesame Street and those who haven't, if that's true, we would say that the likelihood of us pulling a sample of 10 people from each one of these and getting a difference of 8 points would be pretty unlikely. Right. And so because of that, we then conclude that it's likely that sort of groups are probably coming from populations with different average grades. Right. So now if 0 was in there, then we know that we're going to make what decision?
I always get these mixed up, so I'm going to say it in a different way. 0 in there, the null hypothesis is still an option. So
Yeah. Oh, wow. I love how you said that. I was afraid that you would say that the null hypothesis is true, and then I was just going to fall in and pass out with disappointment. But you didn't do that. That's awesome. Yeah, it's an option. Like, I don't know. We're just saying it could be, right? We just don't know. But looking at this, we already know that it's not in there. And so what we can say is anywhere from about a little under 4 to up to 12. Yeah, Emily.
if 0 was in that confidence interval, do we need?
Yeah, I want you to do it just so you can go through the process. But again, this is the strong argument for sort of the over emphasis on t-tests and p-values and things like that. The interval estimate gives you more information. The only thing that you're getting is that specific p-value, which does have value. It's information, right? And so again, if we're thinking about p as a continuous index of evidence against the null hypotheses, then there is sort of information in there, right? But from a practical standpoint, right, if I'm trying to figure out how much fertilizer I need to put on my corn in order for it to grow better than the other field, well, that's giving me a practical sort of number for how much fertilizer I need to put on my corn, right? We've taken this approach and applied it to an area that's all about theoretical construction, things like that. And so it starts to lose some pieces and parts, but essentially this is what we're doing. And probably if we're thinking carefully and wanting to advance science, we should probably get more 2 pounds of fertilizer on my corn stuff, thinking a little bit better. Yeah. Did
You
you?
answered what I was gonna say.
Okay.
I was just gonna say, like, if 0 is not in there, the null is not an option. If 0 is in there, the null could be an option.
Yep. Yep. Exactly. So the only thing I would caution about that is sort of people will say, what we don't want to do is start just taking all those sort of rich information, that confidence interval, and just turning it back to a yes, no decision, right? Thinking carefully about that. Yes. So there's nothing new. You can never have a situation where your confidence bound contains 0 and then you get a different result out of your p-value. It's all the same stuff, right? If that happens, you know you've made a mistake somewhere. All right. So independent sample T, my effect sizes. This is just working through some of the different options that we had provided up there. Here is just our estimate of Hedges G, mean 1 minus mean 2 over our pooled standard deviation. Now, no, please, right? What we first need to do is calculate the variance and then take the pooled variance and then take the square root of that. Do not plug standard deviation units and calculate directly a pooled standard deviation. Mathematically, those are non-equivalent values. And you'll see it. If you take the standard deviation, calculate a pooled standard deviation, and then calculate a pooled variance and take the square root of that, those numbers won't match up, okay? People do this every year. Do not do this. Always start with the variance and then use that to work backwards to get your pooled standard deviation. But if we do that, if we go through and remember that our pooled variance was 20, right? Pretty simple math here. We take our mean difference over the square root of our pooled variance, which gives us this pooled standard deviation estimate, gives us an effect size of 1.79. Right? And Josiah, how would I interpret that effect size?
Pretty large.
What's that?
Pretty large.
Pretty large. Can you give me like a practical, like real world interpretation? What does 1.79 represent? What does that mean? I'm gonna put you on pause. I'm gonna jump over to Basha because Basha looks like she's about ready to jump out of her seat with excitement. Do you know?
I don't know if this is right, but we are 1.79 standard deviations above the, and that means it's really high and good.
I was with you, loving it to the end. Then we started to get a little bit shaky, so it was maybe sort of going beyond, right? But no, you're exactly right. These are just standard deviation units, right? So what I would do is take a look at that and say practically, instead of just saying small, medium, large, which is snooze, who cares about that, right? What we're saying is like literally the Sesame Street group is scoring about 1.8 standard deviations above the average score of individuals exposed to Sesame Street is about 1.8 standard deviations above the mean of those who have not been exposed, right? And that's a lot. That's a big amount, right? Which carries a lot more information than just saying it's big or sort of the value is 1.79. If we're going through and calculating these effect sizes correctly, they contain inherent information that tells us about the actual magnitude. Okay. So this is our Hedges G, but we're also working with sample sizes of 10 or cell sizes of 10 in each group. That's small. Recognize that this is probably an overestimate, right? So what we could do is we can take that value and sort of attach my correction value here, 1 minus 3 over 4 times 10 plus 10 minus 10 plus 10 minus 2 minus 1, drops us down, not a ton, still pretty big, but we're down to 1.71 if we were to apply Hedges correction. which is probably the better bet, sort of given this number of people we're working with here, okay? We could also calculate Glass's delta, okay? In this situation, who might be the better reference group? What do you think, Teresa? Yeah, if we say that the group that didn't watch Sesame Street, this is just kind of our reference group. This is the state of affairs absent presence of quality public television programming, right? So this is kind of where they're at. So we could make an argument to say, yeah, maybe Glass's delta is the best sort of way to go through. And what I could say here is that what we're seeing here is that in the high school students who were previously exposed to Sesame Street are scoring 1.9 standard deviations above the mean of average of students who haven't been exposed relative to sort of variability we would expect within sort of that population, something like that. Yeah.
Is there a way to add in like a correction factor for Glass's delta the way there is with it? Wanting to correct you.
You would just say that you're using sort of unbiased. We could talk about this as unbiased G. So, and probably I wouldn't even worry about that. I would just sort of in your sort of write-up, you can just sort of indicate that you've sort of gone through and done that. I do this a lot when I'm sort of writing up publications. I'll just put in a footnote that says, talk about what I use as my standardizer for my effects, or in the analytic plan, just tack on a sentence that talks about how I went through and did it, which starts to become important because there's just a lot of ways that you can go through and standardize, and it can start to have a pretty big impact on what that point estimate is of your effect size. So it's good to communicate to people how exactly you've gone through and done that. All right. And then finally, get to our independent sample T, right? Independent samples T is like the star of the show, right? It's like sort of the most popular kid in high school, but now we're all 40 and no one actually cares about that one so much, but still do it because make them feel good, right? Whatever. So down here, we got sort of our t-test. Again, just the difference between our two means over our standard error. We already calculated our standard error, so we need to calculate it for our confidence bound. So we know that was 2. We go through, calculate that. We got our test statistic, p-value associated with 0.0008. That's a pretty small p-value, right? What we can then do is take that and go through and calculate that S value in the Bayes factor bound that we talked about, right? So here our S is just the natural log of P over the natural log of 2, whatever that absolute value is. So we've got the natural log of 0.0008 over the natural log of 2, gives me a value of 10.29, which I then round to integer sort of down, right? So it's 10. So that's basically saying sort of evidence against the null in these data, despite the small sample, would be about equivalent as me going through and flipping 10 consecutive heads and trying to tell you that that's a fair coin. I'd probably be pretty suspicious about that, right? Our Bayes factor, same thing, 1 over negative base E times P times the natural log of P. This is base E to 3 decimals. Here's our P value, the natural log of that gives us a value of 64.49. Right? So we're saying that based on these data, at best, sort of the odds of the alternate hypotheses are about 65 times that of the null, which is pretty impressive, right? Remembering that that's a sort of a huge high end estimate, but still sort of talking about, we at least have evidence that if we were to, pretty compelling evidence that these two groups are probably not sharing, that these two populations are probably not sharing a common mean, even though we've got a pretty small sample. All right, questions about anything that we've gone through and done with any of these calculations, or how we've gone through and stepped through this stuff? Okay, cool. So pulling this all together. Here, we've got our null, right? The mean grade of high school students exposed to Sesame Street and high school students not exposed to Sesame Street is equal across their respective populations, okay? Again, note what I've done here is sort of make sure that I'm orienting sort of the reader, let them know that we're talking about populations, not two samples, because I don't need to run a test to see if the sample means are identical. I can just look at them and say, yeah, they are, no, they aren't. What we're trying to do is saying, are these, do we have evidence of equal or evidence against equal population means? Here's null, alternate, pretty straightforward. our confidence interval, our effect size. Now, you don't need to go through and calculate all possible effect sizes unless I explicitly ask you to. I'll probably say, hey, go through and calculate, choose an effect size, and then give me a justification for why you think that one was the most appropriate for this study, this context. Here we've got our critical T, our test statistic, our p-value. Here, our S value, talking and sort of giving a practical interpretation of that S value, kind of what that means. Our Bayes factor, sort of explaining that. And then down here, this is kind of pulling it all together, okay? So here we're saying high school students reporting exposure to Sesame Street in childhood demonstrate an 8-point increase in average grade as compared to high school students with no prior exposure to the program. The difference observed in these data is consistent with a 1.7 standard deviation increase in performance relative to students with no Sesame Street exposure. And I'm just sort of saying, indicating here that I'm sort of basing that off of our unbiased G. Estimates of the population difference compatible with these data range from 3.8 to 12.2 points. Despite the small sample available for the study, results of an independent sample t-test provide relatively strong evidence of greater academic performance in students exposed to Sesame Street in childhood. I'll list out all of our stuff, right? Although the methodology of the study requires additional scrutiny, like I don't know how did they get these students? Was there any type of controls? There's all sorts of stuff that third, fourth, fifth, sixth, seventh, eighth, ninth variables that could start to influence who was exposed and sort of what is exposure to Sesame Street probably is likely a proxy. Not saying that it's maybe not useful, but that's a pretty massive effect size for, if this is true, if this holds up as a causal thing, have everybody just watch Sesame Street as part of, like, sort of forget kindergarten, just watch that, right? Probably not the case. So we want to sort of temper our conclusions. But we say the current data suggests that early exposure to educational programming could be associated with a 2/5 or over a 4-letter grade increase in exam scores. Okay. If we go through and take a look at kind of what I've tried to sort of model here, I didn't sort of go through and I did a bunch of stuff that was cool in animation and things. So asking about how much, right? We've got an 8-point increase. This is telling you if we know anything about grades, and you all know anything, 8 points, 8-point increase in average GPA. That's pretty huge, right? Like that has practical meaning, right? Sort of difference, and then we've got a standard estimate here, ranging sort of precision, an estimate of precision, 3.8 to 12.2, right? That's a pretty wide band, but we also have 10 people in each group, so we're expecting our estimates to not be terribly precise. We've got evidence against the null that we're pulling in here, and then here, important, we've got a practical interpretation. What does this mean in terms of the question at hand? Well, we're saying we don't know a whole lot about the methodology, right? We would probably need to go through and tease that apart because there's probably other stuff going on. But at least in these data are showing at least evidence for, if we look at the mean GPA in this population versus the mean GPA in this population, there's something going on here. Would be premature, wildly premature to say, yeah, this is a causal effect of educational programming, but it's at least saying that there's probably something there, right? Okay, questions about sort of this process of working through our t-tests? Yeah.
So if we're reporting the G value, report D equals
What's that now?
if we're reporting the G value that was given here, the unbiased,
Yeah.
Hedges unbiased G, then we do not need to report the Cohen's D value because the Hedges unbiased.
Yeah, this is telling me you've decided that this is sort of the best metric for this problem, and probably in your assignments I'll say, like, tell me what you're using as your standardizer and justify it, right, to me. Yep. Other questions? Okay, people kind of getting a sense of sort of this process of the independent sample and sort of how we're kind of taking this data, knitting it together. All right, awesome. But we've got a problem. Okay. What if, now our formal assumption of our test is that we have homogeneity of variance, that the populations from which I'm drawing my samples from have equal variability, but what if they don't? What if I have pretty clear evidence from my data that likely population and population A and population B have whatever I'm measuring have different levels of variability. Okay. Problem is that all of a sudden the sampling distribution, my test statistic, all this stuff we were talking about over here is now out the window, right? Because this assumes that I'm pulling samples from populations with equal variance. If they don't have equal variance, I can still calculate my test statistic. I just now start to become very nervous about comparing it to sort of those critical values that we pull, because those critical values are based on a distribution that assume homogeneity variance. And if I violated that, now I don't have a T statistic. I've got what we could call a T prime statistic. This is a different statistic with a different distribution. And the problem is if I take that t-test and compare it with a distribution where I've assumed equal population variance, now I start to be, I'm taking this thing as an apples and oranges comparison, right? Or say maybe a oranges and nectarine comparison. I don't, it's still kind of part of the same family. I just don't know if this is the right sort of comparison to go through it and test against, okay? And so some solutions here, because this is obviously going to happen. Not everything that we want to compare is always going to have equal variance, right? It's actually not going to have equal variance a lot of the time. So back in our past, we had a Behrens-Fisher approach, right? And so what this was is someone going through and calculating table distributions of of our T distributions pulled from populations with different variances, right? Which is okay, but the problem is that doesn't account for all the possible different ways that population variances can differ from one another and things along those lines. And so when we're cranking out everything by hand, it was a solution, not a very efficient solution for today. So we've got some limitations here. And so what we see now in most programming, anytime we sort of will go through and ask for a corrected statistic given violations of homogeneity variance, what we'll see is something known as a Welch-Satterthwaite solution here. Here, what we've done is we've taken whatever T statistic that we've calculated based on our sample data, but we have evidence of unequal variances in our respective populations. We're still interpreting that T statistic as following a T distribution. We just don't know what T distribution it's following. Right, the numbers say it should be following a T distribution with 18 degrees of freedom. But if we've got violations of homogeneity of variance, we know that this T statistic doesn't follow that distribution because of that violation. And so what the Welch-Satterthwaite solution does is it tries to estimate, approximate the degrees of freedom as a function of your sample variances and sample sizes of each group. And so basically what we're doing is we're saying, I've calculated a test statistic that doesn't probably follow the table things that I've got, but I'm still assuming that it follows a T distribution. I'm just going to go through and make an adjustment to try and sort of approximate what family of the T distribution this falls on. So it's not going to be 18 degrees of freedom. Basically, I'm just making an adjustment on sort of the degrees of freedom to go through and say, okay, sort of get maybe a little bit better estimate of sort of that P value. And so what we do here to go through and our formal test that we use to determine whether or not we have evidence of violation of homogeneity of variance is something known as our Levene's test, okay? Levene's test is pretty straightforward. Basically what it's doing is taking for each group, you're taking each mean or sort of each value or each observation in that group and subtracting its sample mean, right? And then taking the absolute or the squared value of that. So I've basically got deviation scores for group 1 and deviation scores from group 2. Then I'm just running an independent sample t-test on the mean deviation score. And if I find evidence of a mean difference in those deviation scores, then I'm going to assume that there's unequal variance, right? So we're just taking a t-test and repurposing it slightly to go through and run a test to determine whether or not I have evidence of unequal variances. Okay, so it's a pretty simple solution, but what we want to do is go through and say, do I have evidence of a violation? If I do, then I need to go through and start thinking about a corrected statistic. Now, early on in this class, what I would have you do is calculate this all by hand, which is kind of a fun exercise. but the formula is quite large for that. There's in the grand scheme of things, recognizing it's probably not sort of terribly useful because your need to calculate that by hand is probably never. So we cut that out. But essentially what we've done, if we have evidence of a violation of homogeneity of variance, what we're doing is we're just calculating our test statistic and comparing it to a different reference distribution with an adjusted degrees of freedom and running our stuff from there. Okay, but our Levine's test is what we'll take a look at to try and decide, do we have evidence for a violation of homogeneity of variance? Questions? All right. So thinking about when I have violations of assumptions and what does this mean, right? The good news is our means-based tests tend to be pretty robust to violations, okay? If I have different variances, right, but relatively equal sample sizes, pretty good there, right? So I've got one group that's got a lot more variability than the other group, but relatively equal sample sizes, I'm pretty good, okay? If I've got some weird non-normality in my observed scores, and I've got reasonable sample sizes and distributions that are similarly shaped, we're pretty good there, right? So if I've got two samples where I'm looking at aggression scores in this group and that group, and that's obviously going to be something that has a strong positive skew, as long as I've got decent sample sizes for that, it's probably not going to make that big of a difference, right? Our tests are generally robust. Now, if I find that I have a strong positive skew in one direction and a strong negative skew in the other direction, then that starts to fool around with stuff, right? But it's rare that we would run something where we have sort of opposite skewed distributions, something to keep aware of, but we're generally okay, all right? Where we start to run into problems is when we start doubling down on violations. So if I have data with different shape and unequal variance, I start to become concerned about the reliability of my tests. Okay, so if I've got one sample, I got a real strong positive skew, the other sample, a real strong negative skew, and then I also have different variance estimates in that can start to cause problems, okay? If I have unequal variances and unequal sample sizes, that starts to create problems, right? I've got a violation of homogeneity of variance, but I've got 20 people in this group and 200 in the other group, right? What happens is larger sample with the larger variance is going to produce too conservative a test, right? If the larger sample is going to get weighted more heavily in determining my pooled variance, which is going to go into my estimate of my standard error. If that's too big, then it's going to make my standard error larger. It's going to drive down my test, and so I'm going to have a conservative test. If my larger sample has smaller variance, now all of a sudden that's going to be overweighted in the estimate on my pooled variance, which is going to go into my standard error. It's going to make that standard error too small, and now I've got too liberal a test, right? I'm going to sort of have a bigger test statistic than I want. So not only recognizing when these things come up, but recognizing the likely impact that that'll have on our tests starts to add in some additional interpretive value. If I've got violations of normality and small sample sizes, right? So again, what is my technical, I'm speaking in technical terms, what is my my normality assumption in my means-based test? Do I have an assumption about the observed distribution of my scores? No, what is it, Sam? Yeah. Exactly. So my normality distribution is about the distribution of sample means. But if I've got really small samples and really wacky distributions that are kind of skewed or have extreme values and stuff like that, I start to worry about the effect that those individual observations can have and start dragging around my means. And so if I've got violations of normality and small samples, I start to become concerned. Now, if I get samples 25, 30-ish, I start to become less concerned about that. So it doesn't have to be huge, but a lot of times we're still seeing studies with really small samples. And so we just have to be sort of aware that what this does is it starts to erode the confidence in my test statistic. Again, the test statistic is based on sort of normal rules of baseball. But now if I have extra people out there or people sort of not out there, people are using corked bats and not corked bats, sort of my decision on who's better than who starts to go out the window because I'm not playing by the rules. Okay. And that's what's going on with this stuff here. Questions about our violations? Yeah. Uh-huh.
Is there?
So run that by me again.
So is there a difference between replacing the scores with their deviation?
Yeah. So mean centering, that's going to be a different thing. We're going to get that in. We're going to get into mean centering when we get into regression stuff.
Okay.
But mean centering, all that's going to do is that's just going to impact, sort of facilitate our interpretations. So the Levine's test is just saying, on average, how far do scores in this group deviate from the group average versus how much do scores in this group deviate from the group average. If they deviate about the same, those two deviation numbers should be about the same. And so we should not get a significant test. But if they are different, right, if they scores in this group vary sort of widely from the mean, whereas they don't in this other group, they're all kind of tight around the mean, then what we're going to get is we're going to get a low p-value on that. We're going to get a significant test, but this is a case where we don't want the significant test because that tells us that we've got a violation. Does that help? Yeah. Okay. Yeah. Other questions? All right. So what we're going to do, pop open that MBA t-test data set. We're going to go through an example here. We say investigators are interested in gender differences in marital satisfaction for motor vehicle accident survivors committed to long-term heterosexual relationships. Okay. So we've got 22 women and 5 men meeting diagnostic criteria for PTSD subsequent to motor vehicle trauma. These individuals are completing the Locke-Wallace marital adjustment score test. Scores are going to range from 2 to 158. Higher values indicating greater marital satisfaction. Participants are also going to complete the Marlowe-Clarence social desirability to assess differences in socially desirable responding across men and women survivors. Based on previous research, investigators hypothesized that women will report greater levels of marital satisfaction than men. Tendency towards social desirability expected to be similar across groups. For this example, we've got all the stuff that we've been doing, so we want to go through and walk through this stuff. Okay. So if you've got your data sets open, what we want to do is start with the screening. Okay. Drop this down. Okay. Cool. And if you're wanting to follow along with the screening in your handouts, it's just our independent sample t-test screening form right here. Okay. So first thing we have to do, right? So just like we did with our independent sample test or our sort of single sample test, what we're going to do is we're going to go through and we want to go through and take a look at our distributions. But what's different from our independent sample or sort of our single sample test versus our independent sample test? What do you think, Amanda? Yeah, I've got 2 different populations, right? The first time I just had 1 population. Now I've got 2 populations. I've got to go through and handle that because if I don't sort of separate my scores, then I'm going to get distributions or histograms, box plots that have everybody in there, but that's not what I'm wanting to do. I'm wanting to look at these individually. I want to look at them separately, right? So the first thing that we're going to do, maybe what we'll do first is go through and first take a look. It looks like we have some missing values. So what I'm going to do is I'm going to sort ascending with my Locke-Wallace, right? I say, oh, person 132 is missing Locke-Wallace, and they're also missing a Marlowe-Crown score, right? So I'm going to record that somewhere, make sure that I sort of note that case number 132 is missing scores. Same thing if I sort Marlowe Crown, same thing's going on, right? So what I'm going to do is I'm going to go file, save as, I'm just going to call this my scrap file. Yeah. Okay. So I'm going to make sure that I mark down somewhere that 132, who was, if I go through and I took a look at my, so 1 is male, 2 is female. Okay, so I've got 1 woman, case 132, someone in my women group is missing scores, sort of mark that down, and then we can go through and get rid of that person there. Okay. Also want to go through and take a quick look at plausibility of my scores, right? We say that our Locke-Wallace ranges from 2 to 158. Okay, that tracks. Looks like everything's within bounds there. My Marlowe Crown, if I sort those, 10 to 26, 0 to 33. Okay, that tracks. So I've gone through just right off the bat, taking a look for missing data, plausibility of scores. So right now things are looking okay. Okay, so go through, make sure I take note of that. So now what I'm going to do is I'm going to go to data. I'm going to go to split file, not split into files, but split file. And click that. And then what I'm going to do is I'm going to compare groups based on gender. Okay, because this is my grouping variable. We're sex, gender, sort of here, we're sort of biological sex, what this is going through. So we've got men and women, and we're going to go through and split these files in SPSS. What this is going to do from here on out, when I split this file, anytime I go through and run a statistic, it's going to run it separately for men. It's going to run it separately for women. That way I'll get different scores, and I can go through, I can look at distributions, extreme values, things along those lines separately within these groups. Very, very important. If you don't do this, what you're going to get is standardized scores, distribution that contains everybody. That's not what we want, right? We want to look at these distributions separately across our samples from our 2 populations. Okay, so I'm going to go hit paste here. And remember, you can go through here and splitting file by sex or something like that, just so you can remember kind of what you're doing. Anything you put in an asterisk in front of is going to be a comment. It won't get read in terms of your files. Okay. You can go through and run this. All right. So I've gone through and done that. What I want to do now is then go through, and it's just going to be the same stuff that we did with the single sample test, right? I'm going to go to analyze. I'm going to go to descriptives. I'm going to go to descriptives again. Click this. And Matt, what variables do I want to look at descriptives for?
Locke-Wallace and Marlowe Crown.
The Locke-Wallace and the Marlowe Crown, exactly. So I'm going to drop those into my variables. I'm going to go to options. I'm going to ask for skew and kurtosis, okay, just because I want to know those indices. So I'm going to hit OK, continue there. And then I'm going to hit save standardized values as variables. Basha, why am I saving standardized values as variables? What am I going to use those for? Emily, you want to help her out? Those are my Z-scores. Yeah, and why am I interested in Z-scores? Is my distribution of my Z-scores going to be any different than my observed data? No. What? Yeah. Okay. So it's transforming them into Z-scores where I can look. So this is what I'm going to use as sort of an objective metric of extreme values to see how far out there. I can say like sort of how far relative to the rest of things are my samples. But remember that we went through and we split this file first, and that's important because if we don't split the file first, what it's going to do is it's going to create Z-scores based on the full sample average, which is going to be different than it's creating Z-scores separately for men and women, so they're using their respective group means for that. So we always want to be careful when you're going through and running this. Okay, so we're gonna go through and hit paste so that we have a documentation of that. All right, and then if I run through my descriptives here and run that, should get a, okay. This is kind of small up here. I don't know how to, can't, oh, maybe I can. Nope. That's a search, not a magnifying glass. Damn it. Okay. What are we seeing? Sam, if you're looking at, you got this output on your screen so you can see, okay. What are we seeing here in this output? Let's start with the men. What are you seeing up there?
First of all, they're anti-Semitic.
Yeah, so they've got us, you only got five, we got 5 dudes in this group. That's not great, right? That's super small. That's going to be something we want to hit on sort of for sure, right? So we've got a small sample. What else?
First glance, it looks like the average first score is lower.
Okay, so, but sort of with this for the screener, so we're not too worried about quite yet about sort of the mean values, right? True in terms of that if we go through and look at a comparison against the women, but are mean statistics falling in sort of what we would expect, or at least reasonable values for these 2 measures? Yeah. Yep, Lock Wallace is looking reasonable.
Trying to find the range for the other measure. Social desirability?
Yeah.
Yeah.
Yeah. Okay, so yep, both of these are looking reasonable, right? And we already knew that because we went down through and sort of checked to make sure that we had plausible values, but always good. The more spell checks you can have in there to go through and take a look at. Now, if I use these measures a lot, I might think they're funky or screwy or something like that, but at least based in terms of like what this can fall in, looking okay there. Okay, what about if I'm looking at my skew and kurtosis values here, Sam? What am I, do I have any concerns? Yeah. Uh-huh. Uh-huh.
But I'm failing to recall like how large of a magnitude.
Yeah. What are our benchmarks for skew and kurtosis that we've, again, anytime we're talking about benchmarks is very, very rough. Like it's not a hard and fast, but what are kind of the values that we were thinking about? Remember?
Around like 1, -1.
2 plus or minus 2 is kind of about what people are, you know, and again, this carries very little meaning at all, but it kind of one of those benchmarks you'd be like, okay, is this starting to show sort of major deviations from the mean? And so if I look here, skew is not too bad. I mean, in terms of absolute value of these indices, that's fine. Not anything I'm too concerned about. Kurtosis values are negative, so negative 2.5, 2.25, right? And so what does that negative kurtosis tell us about the shape of this distribution? Yeah, it's kind of blocky. It's kind of boxy, right? So it's not great. And so we have some elevated negative kurtosis, but what's maybe happening? What's maybe driving some of that? The sample size. Yeah, I got all of 5 people in here, right? It's hard to get a really nice normal distribution with 5 scores. So I'm taking that into account, but I'm probably not going to freak out quite yet. And you should probably not freak out about that level too much, but we're noting it. Okay. And then Sam, take us home. What about for the ladies here? Sort of what are the women doing in terms of their stuff?
So again, we have some
values or kurtosis, I don't think there is.
Yeah. So not doing too bad. Values are still falling within bounds. Sample size is still small. It's a hell of a lot bigger than the men. We're still talking about a sample of 20-ish, right? And so we're still not super excited about sort of what we should expect in terms of the precision of our tests here. Right? Okay, but so we've gone through taking some notes there. What's the next thing we want to do? Amanda? Yeah, I want to look visually, just see what these data are looking like, right? So what I'm going to do is I'm going to go in, and before I do this, I'm just going to unsort this. So if I go or unsplit the file. Now you can go through in, we could go to data, split file, and we could say analyze all cases, do not create groups, right? And so if I do go through and I paste that, we'll see I've got split file off that command, right? But what I can also do is I can just go through and sort by participant number, and that's gonna, anytime I sort the data, it's gonna take that split file off, okay? So either way you wanna do it, I just will usually sort things if I don't want that split file on there, right? So I just went through and sorted. Now I'm gonna go analyze, I'm gonna go to descriptive statistics, and this time I'm gonna go down to explore, okay? This is gonna give me a little bit of a shortcut to getting some of the graphs that I want, as opposed to just going through the graphical interface that we did last time, okay? So what I'm gonna do on my dependent list, I'm gonna enter my Lock-Wallace scores and my Marlowe-Crown scores, okay? These are my two outcomes that I want graphs for, okay? Then I'm gonna go through in this factor list. What this is gonna do is it's gonna split up these histograms by whatever grouping variable I drop in there, okay? And because we're running an independent sample t-test, what I'm gonna do is I'm gonna take my gender variable and drop it into my factor list, because now what this is gonna do is it's gonna give me separate histograms, separate box plots for both of my groups. Just kind of a nice, efficient way to get this. And then the last thing I'm gonna do on this label cases by, I'm gonna take my ID number, my subject number down here, and then I'm gonna drop it down here, okay? What this does is it's gonna go through in our box plots. If I have extreme values, it's gonna attach a participant number to that data point, which is nice because it tells me exactly which point is falling out there. Eyes on me, look at me. If you don't do this, you can still run it. But what SPSS is gonna do is it's gonna label those points as where they fall in the case. So it's gonna give it this. So you'll see case number 18. That's just where that falls in the line, not the participant number. What'll happen is you'll get that screwed up, and then you'll say participant 18 was an outlier in the box plot, but there is no 18 on here, right? So you'll have identified the wrong thing. So just know that that's gonna happen. But we're gonna go through, drop subject number in, and then under plots, I'm gonna turn off stem and leaf. I'm gonna click histogram. I'm gonna hit continue. I'm gonna hit paste. Okay. So now what I'm gonna do, if I go through and I run this, what it's gonna do is it's gonna give me a whole bunch of statistics that I don't really care about sort of necessarily, although if I do need them, it's nice to have them in here. What we've got is a processing summary, sort of making sure that my numbers line up to what I'm expecting, right? So I've got 5 men, 21 women for both, no missing values, cool. That's what should be going on here, right? But then if I go down, what it'll do, it'll give me my histogram for my men, histogram for my women, box plots across my two, and then histogram for my Marlowe crown for men, histogram for my Marlowe crown, or my Marlowe crown for women, and then the box plot of the two. Okay. So if I go up, take a look, Katie, what do I think about this box plot for the men? It doesn't look that great, right? But I've got 5 people in there, so this is never going to look that great, right? I might talk about this as a square distribution, sort of influenced primarily by sort of having only 5 people in the sample, right? If I go down and I take a look at the distribution for my women, looks a little bit better, right? You got more people here. Basha, how would you describe this distribution?
Kind of like bimodal, honestly.
Yeah.
I don't know.
No, you're exactly right. It looks kind of bimodal. Now, it's hard to tell whether or not with only 21 people in here, how much sort of that actually impacts. But what are we measuring here? What's the actual construct we're measuring? Marital adjustment, marital satisfaction. Why might we get a bimodal distribution in marital satisfaction following some sort of traumatic stressor? What might account for what we're seeing here? Anybody? Yeah.
An adjustment that is going to either be very hard for some individuals or easier, so the adjustment is going to be lower or higher.
Yeah, so we're talking about marital satisfaction here. So maybe what's going on is I might have people who have a supportive partner and then people who don't have a supportive partner. Anytime I see a bimodal distribution, like now I'm not putting too much into it because we don't have that many people. This could be just a random fluctuation in the data, but thinking about sort of marital satisfaction, relationship satisfaction after a stressor, what I might be seeing is something that's looking at, so I've got kind of actually a heterogeneous group here, sort of a couple different populations, people who are sort of in sort of a supportive relationship and those aren't, and that's what's maybe driving some of this stuff. I don't know. We can't sort of make any determination or know based on the data that we have, but it might be a hypothesis that I'm running in my head to just kind of understand sort of what's happening in our data. Okay. So if we go down through, take a look at our box plots, we're seeing median values, certainly different median values in terms of satisfaction among our women relative to our men. Nothing too much going on. Looks like the men, really even distribution here, not much interesting going on. Maybe a slight negative skew for marital satisfaction in my female survivors, but we've got to go through and make a description there. Same thing, social desirability. I've got 5 people, so that looks like a ridiculous kind of square distribution. There's not much we can say about that because we don't have enough people to sort of really put together a meaningful distribution. For social desirability for the women, that just kind of, it looks fine. It's about what I would expect from a distribution with 20 people in it, right? Again, looking at my social desirability scores across my male and female survivors, looks like a little bit more negative skew here. Maybe some slightly different terms in median values, but sort of nothing too bad with stuff. Okay. Questions about this? Sam, Elizabeth, are you sort of kind of on? So, okay.
Yeah. I think it's the box plot, so we were trying to.
Oh, yeah.
Not the box plot, but mine are aligned like this are, mine are just female and then male. So I was trying to figure out if I done something wrong. But
Yeah, if you don't take the split file off, it'll sort of return you in there. Okay, you got it? All right, cool. All right. So we've gone through taking a look at our distributions. What's the last thing we want to go through and do here? What do we want to look at? Yeah, someone say it loud and proud. I heard someone whispering it. Say it. Z-scores, yeah. confident in your wrongness, even if it is, right? Yeah, we want to look at z-scores, okay? So what I can do is go back through, and I'm going to go to analyze descriptive statistics, go down to descriptives. You can get rid of my raw scores here and drop in my 2 z-scores, okay? I'm going to go to options. I'm going to turn off skew and kurtosis. I don't need skew and kurtosis on z-scores. It's just going to be the same as my raw scores. I'm going to unclick save standardized values as variables because I don't need z-scores in my z-scores. And then I'm going to go through and I'm going to hit paste, okay? But what should I do before I before I start looking at my descriptives for my z-scores? Yeah. Not so split them. Yeah, want to split them again, right? But what I do, I don't have to, instead of wandering through SPSS menus, I already have my command for my split file, right? So I'm just going to run my split file and then come through and run my descriptives here. Okay. Now, once again, if I've done this correctly, what should my mean and standard deviation be for my z-scores? 0 and 1. If it's not exactly 0, it's not exactly 1, you've probably gone through and created z-scores based on the mean of the whole sample and sort of done some stuff up there. This is a nice double check, okay? But if I'm looking at these z-scores, sort of the min and the max, Josiah, what am I saying about this? Or sort of what might be my conclusions based on all of this?
So it looks like your minimum max for your min is about over 1 standard deviation and almost 2 standard deviations. Wider range.
Okay. So we've got some differences, but in terms of extreme values, anything that's sort of standing out at me and screaming sort of red alert, probably not too much, right? So when we already know that kind of based on sort of what we've gone through and taking a look at the histogram, right? This is just giving us some sort of objective metric so that we can communicate that so that people don't have to take my word for it, right? I don't want anybody to have to take my word for it. I'm going to say, well, here's what I see in terms of the distribution, in terms of the histograms, of box plots, but here's sort of objective measures so you can go through and make your own decision. Okay. So there's one more thing. What's the other assumption that we had with this test that we haven't gone through and taken care of yet? Their independent sample t-test. Yeah, Emily? Okay, we're going to go through and calculate those for sure, but thinking about sort of underlying assumptions of the test. What did we add in? Yeah, Sam. Okay, yeah, homogeneity of variance. Yep. So we haven't gotten that here. What we'll get there is we'll get that in our actual, when we run the test. So we'll loop that back in, but based on the stuff that we've done thus far, we can go through and sort of our write-up. Oh, are you kidding me? Okay. Oh boy. I'm not interested in a tour. All right. So something along, and this, you have this handout, right? So what we can say is marching through our screening here, we've got our missing data. We notice case 132, we've got a woman on our sample where we're missing scores for. So we just want to take a note of that. We've got plausibility for Marlowe-Crown or Locke-Wallace within reasonable bounds, right? What we probably want to do is add in here and say that sort of like we did in the previous one, say, hey, we got rid of that one person. So we've got now a functional sample of 26, kind of drop that in there. In terms of distribution, skew values for the Locke-Wallace and Marlowe-Crown within acceptable bounds, negative kurtosis for both variables. So again, I'm sort of identifying my variables and dropping in my values for my skew and kurtosis here. So we're communicating that. Histograms indicate square distributions, box plots symmetrical, no values falling out beyond 1.5 times in our quartile range. Box plot of Marlowe-Crown consistent with mild negative skew, no extreme values, just kind of describing that. Same thing for our women. skewing or kurtosis values within acceptable bounds, histograms, some evidence of negative skew, otherwise unremarkable, not too much going on. Box plots reasonably symmetrical with no values falling outside 1.5 times in a quartile range. Right? If you wanted to make a note and sort of give some ideas about sort of that potential bimodal distribution, you could, right? But it's not necessarily relevant for sort of the functional screening, but probably something that's kind of good to pick up on. Outliers, extreme values, standardized scores for lock wall, smaller crown, falling within plus or minus 2 standard deviations for both male and female samples, right? So we've got Z-score kind of put in the max, so absolute value, because these can go either way. Homogeneity of variance, we'll talk about that in a minute when we get into the test, but then say initial screening, notable difference in the number of males and females. So again, this is where you're kind of pulling things together and saying, like, as your consultant, this is what I'm saying is possible hiccups, right? Unbalanced design, expected to have negative impact on statistical power and robustness of the test. Distributions were generally acceptable, skew and kurtosis slightly elevated, but likely associated with the number of people we have in that sample. Here we're talking about Levine's test. So we're saying, well, test failed to meet acceptable criteria for statistical significance for the Levine's test. It's probably because of the small sample. We'll talk about that. So we're just kind of going through and pulling this stuff together to just kind of say, hey, this is what our data are looking like. This is the type of stuff that we should probably keep in mind as we're moving through our test. Okay. Oftentimes applied statistics is making the best of a bad situation. We just want to know in the screening up front, hey, these are the warts. This is what you should probably keep an eye on. These are the limitations of our inference. So just know that moving forward with stuff. Okay. All right, cool. Thanks for hanging in there with me. Let's take a break and come back just a little before, just a few minutes before 4. Okay. All right.
This doesn't match.
Is it a different one? Ah,
It's like relatively the same information.
okay.
I have that hand up if you want to compare.
Well, I gotta. All right, you guys take a break. I'll figure this out.
Okay. Ours just has bullet points for recommendations. It doesn't have a summary.
Oh, okay. Yeah, do that. That's better.
Yeah, 'cause I can show you whatever it's like that. It's like bullet
Okay,
points.
yeah, that's, yeah. The one you have is, I copied the wrong one now to this, so, yeah. This is easier because you're going down through and kind of bulleting that, so it kind of summarizes things and then puts it
Cool,
together.
yeah.
So, yeah,
I was noticing that because like all the words were, it was
yeah,
the same but different. And I was like, what is
Yeah.
that?
all right. So after we've gone through and done all sort of those things, what we want to do, we're finally at the point where we can go through and start running our actual test. Yeah, Emily?
Sorry, really quick, just going back,
Yeah.
Okay.
Homogeneity and variance and Levine's test is going to come when we run the actual analyses. So we'll just go through, so we'll screen stuff, then run the test, get that homogeneity test, and then sort of roll that back into the screener.
Got it.
Okay.
Cool. I thought I-
Yeah. So what we're going to do, we're going to run our tests. So we're going to go to analyze, go down to compare means. We're going to independent sample t-test. Choose that. Okay. And my test variables, interested in my Locke Wallace and my Marlowe Crown. Drop that in there. And then my grouping variable, be gender. Then I need to define my groups, right? My groups here, it's already, SPSS has already populated it. I've got 1 is my men, 2 is my women. Make sure that those are sort of where they need to be. So I'm gonna hit continue. I'm gonna leave this estimate of effect size box checked. And yeah, that's it. There's nothing else. I could change my confidence intervals if I wanted different confidence intervals or something like that, but we're looking good. So I'm gonna go through, I'm gonna hit paste. Make sure that my, here, so I don't get an error. I'm gonna sort my variables because I had that where I left off. I had the split file on. If I try and run my test with it, the file split, it's not gonna have anything to compare to. So you'll forget that at some point and it'll come up and you get an error. Remember that you just have to go through, unsplit your file so that you actually have groups to compare. And then we're going to go through and run this. And what we'll do is I'm just going to pop back over to our slides just because it'll be, no, it won't be easier to see it there because that's even tinier. Okay. All right. So what are we seeing here in terms, oh, well, first let's go up to our group statistics, okay? Anytime we run this, always want to go through, take a look at your group statistics. You've already gone through and done this because you've screened your data. You just want to make sure that everything is looking even, Steven, that you're actually comparing the groups that you're trying to compare to, okay? So we've done that, and now we drop down into our independent sample t-tests, okay? So if we're going through and taking a look at our independent sample tests, we see our Locke Wallace. All right, and so what we've got here in this first box is this Levine's test for equality of variances. Okay. And so I see for my Locke Wallace total, here's an F value and here's a P value. Okay. Josiah, what is this telling me about sort of my homogeneity of variance test?
Is this in standard deviation?
What's that?
Is it standard deviations?
Yeah, so it's basically a comparison of the sort of variances. Yeah.
So equal variance 2. So that's saying that the Locke Wallace, this could, student is comparing the men and the women that we did to the variance between and the woman in the Locke Wallace. A third or so standard deviation. But between the Marlowe Crown, it's more like 4 standard deviation.
Okay. So you're on the right track. Okay. So these F statistics, these are our test statistics. So these probably don't have sort of like right now for you all sort of anything that's has a practical interpretation, but I love that you're attaching, think about practical interpretations. This is just going through and testing to say, do we have evidence of, do these data provide evidence of different population variances? Okay. And so we have a very large p-value, 0.569. And so what does that say if we have a large p-value? It says we don't have evidence against the null, right? And in this case, what's the null? That the variances are equal, right? So are we liking this large p-value for this? Yes, we are. Why are we liking this large p-value, Emily? Yeah, yeah. I mean, so we don't have a whole lot of skin in the game on this because if we do have evidence of a violation of homogeneity variance, we can just drop down to this equal variance is not assumed line. So we're fine. But in general, what this is saying is that based on this test, based on my Levine's test, it's saying that I don't have really any evidence for likely difference in terms of the respective population variances. So basically what this large p-value is saying is that we don't have a violation of our assumption. Right. This is one of these times where if we do have a small p-value, it's not so great because it's indicating that the difference in these two groups, the variability in these two groups is likely not 0, but we kind of want it to be, right? So here for the Locke Wallace, we don't have, so our Levine's test is looking okay. So what we're going to do is we're just going to proceed with equal variance is assumed and just interpret this line here. Okay. So we have a test statistic. Here's our T. Here's our degrees of freedom. We're going to ignore the one-sided P. We're looking at our p-value. We've got a p-value of 0.033. Okay. So it's not super small, but it's sort of below our conventional threshold, right? Here's our mean difference between our two groups. Now recognize that this is kind of the sign on this is arbitrary. You want to go through and make sure you look at your means and know who's scoring larger than who. And then here's our confidence bounds for this. Okay. So Amanda, what's our decision for our question? Do we have differences across men and women in terms of reported marital satisfaction here? Yeah, we would say that we have at least some evidence of a possible difference in marital satisfaction across men and women survivors, right? Because, I mean, we've got pretty small samples. It's not overly compelling. So, and we'll go through and I'll sort of we'll walk through calculation of our S values and our Bayes factor, but it's at least looking like we've at least maybe got a signal here. Okay. Now, if we drop down to Marlowe crowd, social desirability, okay. We've got our F statistic here, and then we've got a p-value that's 0.054. What do we make of that? Yeah, Emily?
The equal variance is really not assumed.
Okay, so technically, right, if we're saying so this 0.05, do we have clear evidence of differences in variability across the two populations based on these data? Probably not. But what else is going on in this data set? Matt, how many people do I have in this data set?
60 people.
Okay, 26 combined. Is that a lot? No, that's not a lot. And if we don't have a lot of people, and this is a significance test, is this test likely overpowered or underpowered? Underpowered, right? And so the fact that it's even approaching something, I'm not just going to dismiss it out of hand, right? And again, when we're thinking about our tests, always wanting to go through, anytime we're running a test, we want to think about the sensitivity of this test, because a couple of different things can happen. Here, we could just look at this and say, well, that's not below 0.05, and so I'm good to go. I would say, maybe pump the brakes on that a little bit, because we're working with a sample of 5 and 21. So I'm going to take that into account when I'm trying to make an interpretation. Here, looks like there's probably not, or sort of like maybe not a violation, but I don't know. The fact that I'm even getting close with a sample of this size is telling me I might need to sort of take that into consideration. Alternatively, let's say I've got a big sample. I got 151 group and 300 in the other group. And I find that, yes, my Levine's test is sort of less than 0.05. Should I automatically be worried about that? Why not, Emily?
Because you have a lot more people, plus. There's a variance.
Yeah, well, so basically I've got a whole lot of people, right? And if I've got a whole lot of people, Sam, how sensitive is that test? Pretty sensitive, right? And so maybe if I go through with those massive sample sizes, I wouldn't be surprised if I always end up with something that's below p equals 0.05, because like any other test, it's just saying that this difference equals 0. And if it's trivially small, if I go up through and look at my, well, I would square those to look at my variances. And if they're pretty close, I might not worry too much about sort of violations of homogeneity of variance. It could just be I have a incredibly sensitive test that's picking up trivial deviations in my variability. Okay. So again, this is where sort of knowing what these tests are doing and sort of being able to interpret them in context starts to become really important, so that I don't go off on a tangent and sort of start to become super worried about violations of homogeneity of variance, where it would be almost impossible given my sample sizes for something to sort of not trip up as sort of big. Or situations like this where, yeah, that's not less than 0.05, but I'm not super confident that there's not something there. It's a pretty ambiguous test right here, given our sample size. Okay. But if I go through and I take a look at this, it really doesn't matter, because my mean for my Marlowe crown is almost identical here, there really seems to be really nothing much going on in terms of differences. And so I'm not going to be too worried about stuff here. Okay. So saying for my Locke Wallace, looks like I might have a difference where specifically men seem to be reporting lower levels of marital satisfaction than women, at least in this sample. But my social desirability, which is important, right? I want to make sure that sort of rule out the possibility that sort of we just have differences in sort of what I'm willing to, sort of how I present, but it doesn't look like that, at least as an alternative explanation for why I'm doing stuff. Okay. We drop down to our effect sizes down here, right? We got our Cohen's D. This is what we called Hedges G, right? We can say that the Cohen's D uses the pooled standard deviation. So that's just calculating Hedges G, like we've talked about. Hedges correction, this is unbiased. Glasses delta, this is just using probably the men as the control group. I don't know. You just want to go through and sort of take a look and figure out which one is going on. So we've got point estimates for different metrics for the Locke Wallace, and then down for Marlowe Crown. Yeah, we're seeing stuff that's 5/100ths of a standard deviation there that's functionally identical, right? So we're not too worried about that. So questions on how we're interpreting this output, things that we're pulling out of this. Oh, yeah, Emily.
What is the point?
Point estimate is just my figure, right? That's what we're always doing when you're calculating tests and estimating means. It's just my point estimate. It's my value. It's my best guess,
Oh,
right?
okay.
Versus our interval says, so based on my sample, this is my point estimate of the population value, but recognizing with those intervals that anywhere from here to here would be data that are values that are reasonably supported. Yeah.
And so when we're looking at the Cohen's D or whatever one, that's gonna be the one that we're looking at. That's the
Yeah. So that's just using the square root of the pooled variances as my standardizer. So nomenclature is sort of it'll differ. Just make sure that you sort of know what you're talking about when you're pulling that stuff.
standardizer on here and pool variance that we take those the same.
Yeah. So I mean, they're calling it the pooled standard deviation because they've taken the pooled variance and taken the square root of that, right? So yeah, if you look at that at the footnote underneath that table, it helps specify what those variances are. And the other thing you can do, which I always would encourage you to do for when you're working with new statistical software and it's calculating something that says this is what it is, go back through and hand calculate it, see if they match up, right? Because sometimes who knows what's going on in the bowels of these programs. What they're saying might be something very different than what you think it's doing. It's always a good idea to cross-check that with some hand calculations and say, okay, yep, this matches up. I understand how it's going through and calculating, and so I can confidently report. So here is just before SPSS would do this for you, this is what you would have to do on your own. I often touted this as a benefit of Stata, which is what we use in my lab, because Stata will just do this for you. And finally, I've harassed SPSS enough that they've been monitoring my YouTube channel closely. Those folks at IBM, and I finally pushed them into sort of having this, so you can thank me later about that. But if we go through and we calculate effect sizes for our G, or what SPSS is reporting is Cohen's D, and our unbiased G, which is what SPSS is reporting is G, these match up. Same thing for the Marlowe Crown, these match up. So you're just going through and walking through those calculations, matches up nicely, gives us confidence that what we've done is correct and on target with stuff. Here's an example of our write-up. Again, this middle bullet point, ignore that. Please don't put this in your write-ups for your stuff. You've covered this in the screening with the bullet stuff that I've already said to you. I just kept it in there so you could kind of see what this might look like if you were to put to get together in sort of a prose thing, but please don't include that in your write-ups you've already covered in the screening. You don't have to do screening stuff twice. Okay. But down here, so we're saying evaluation of Marlowe Crown scores failed to provide strong evidence for difference in socially desirable responding across male, you have descriptives, and female descriptives survivors. test statistics, right? Independent sample t-test identifies observed data as compatible with null or near null differences in these populations, giving you an assumption of the underlying model, right? We're just saying like, hey, looks like there's not much going on here, right? I'm saying null, near null, specifically in this because the means were almost identical, right? Now, just because you don't find a difference, don't call it null or near null. Like this is very specific to this case, and that we found that like the means were right on top of one another, right? Now, if we look at that confidence bound, it could be anywhere from men could be a lot smaller to a lot bigger, who knows, right? But sort of 0 is kind of dead center in that. So that's why we're calling this null or near null, right? So your results do, however, indicate potential for greater marital satisfaction in female survivors with a point estimate of unbiased G suggesting a full standard deviation increase in scores among women, right? Here, descriptives as compared to men, and then our effect size. Again, just dropping in those descriptive statistics so I can see when you're communicating, like this is literally the mean that we're working with. Confidence bounds, however, identify values ranging from 2.45 to 54.8 as plausible estimates for the true difference in mean satisfaction, right? Worth noting that lower bounds supported by these data not consistent with meaningful differences in sort of thing, right? So we're saying, yeah, data suggests that it could be, but the variability is sort of our estimates support anything from here to here. So yeah, our data is saying that there might be a difference, but sort of magnitude of that difference is really unclear due to the lack of precision in my tests. Right? Independent sample t-test provides only modest evidence for absolute difference in satisfaction in the larger population, right? We've got our F, our S, and our Bayes factor dropped in here. The Bayes factor bound for these data suggests likelihood of alternative hypothesis being at most 3.3 times that of no difference in marital satisfaction across female and male survivors. So just dropping in some stuff about Bayes factor and stuff like that. I don't expect you to sort of do this all the time, but again, what I was trying to do in this is saying, yeah, we did find a p-value that was less than 0.5, but we got to be careful about how excited that we get about this, given all the stuff that's going on. It's tiny samples, likely overestimation of stuff, all those sort of things about the methodology that we don't know about. You got p-values 0.03 that are fine, but certainly not something. I don't know how confident I would be about going through. The fact that we found something with this small of a sample sort of gives us, again, sort of a point estimate of an effect size that's quite large. What do we? An unbiased G of about sort of over a standard deviation difference, right? Going back to Basha, your question, if I were to run this study again, would I expect a sample, an effect size of that large? Probably not, right? I might expect, particularly if I've got a reasonable number of people, I might still expect to find something, but it would probably not be that large, right? The risk that we run into, right, is Elizabeth goes through and says, oh, well, really, if I want to tease apart this difference, I just need 5 men and 20 women, and then I'm going to be good to go. That's not how this works, right? This is likely a huge overestimation of the sample. I'm not saying that there's not, our data suggests that there likely is a difference. It's probably not that big. I would want to have a lot more stuff before I start making any type of conclusive discussions on whether or not we're seeing differences in marital satisfaction among married survivors. All right, so people see how we're kind of pulling this all together and sort of taking all the information that we've calculated and trying to come up with so that I can say something about this, even if that something is that we can't say a lot. Make some sense? Awesome. Okay, cool. And here's kind of a shorter version. You might write up for a publication, something that sort of doesn't have a 4-page results section on an independent sample t-test. We probably won't, editors won't tolerate that, but okay, cool. All right, we're going to finish up by talking about our repeated measures designs. So we talked about our single sample test. We talked about our paired sample or our independent sample test. Our paired samples test. This is where we're taking one group of folks and we're just observing them over a couple of different occasions. Okay. Now I put an asterisk here. And that asterisk is because there are certain situations methodologically when we can use a paired sample test if we're comparing two different groups, okay? This is going to be situations if I have a matched paired design, right? I have sort of one group of sort of my test people, and then I kind of have a comparison group of people that are matched on sort of a bunch of different characteristics or things along those lines. Historically, we've generally taken that to say, hey, this person is identical to that person outside of this one thing that we're interested in, using that as in a matched subjects design. And what we've tended to do is use a paired samples approach to that. That's some old school stuff. Don't see it that much these days, but it's technically, traditionally sort of one of those things that people have done. Okay. So benefits of our repeated measures designs. A lot of the stuff we're interested in just kind of falls in this, like, if I do this to you, what happens, right? If I change this thing, what happens, right? So if I have Katie measured on multiple occasions, I can watch how whatever I'm doing in terms of this experiment, how Katie changes in her responses based on these things. More efficient use of resources. Instead of having two completely different samples, one that gets this and the other gets that, I just have one sample, sort of much more efficient there. And then the increased ability to control or account for random error and variability. If I go through and take a look at everybody who gets my sort of manipulation 1, and then look at and then give them manipulation 2 and see how they change on that, Katie's less likely to change how she systematically goes through and reacts from one time manipulation 1 to manipulation 2 than comparison of Katie in manipulation 1 and Sam in manipulation 2. Because those are two different things. Like, yeah, we gave them different manipulations, but Katie and Sam are different people. They respond to things differently. They're going to be in a different headspace when they show up. There's all this other stuff that starts to go in, and it starts to cloud up the system, right? If there are situations where we can go through and instead of just measuring different groups, we can turn this into a repeated measures design, hugely more powerful, okay? And so here we've got our paired sample test used to look at change in scores within individuals across repeated assessments, okay? And so this is super important for our paired sample test, our unit of measurement, right? The thing that we're going to be running all of our analyses on are these difference scores, okay? T2 minus T1. So your second observation minus your first observation, that's your unit, a difference score, okay? Now in SPSS, you're going to have sort of assessment 1 and assessment 2. They're going to be in different columns. What SPSS is going to do is it's going to, in the background, calculate the difference between those two and then just have it in the memory, and it's going to run all the operations on those different scores, okay? And this starts to become important in understanding what's actually going on with these tests, okay? So our hypotheses for a paired sample test. Our null hypothesis is that the mean of the difference score is equal to 0, okay? Population difference score is 0. If I measure the population on 2 different occasions and I subtract those two, the mean score is going to be equal to 0. There's nothing going on. Our alternative hypothesis being that the mean difference in the population is not equal to 0. Difference in scores is equal to some non-zero value, right? We're not saying if it's getting higher or lower. We're just saying if we measure you once, measure you twice, the difference between those two scores is some value other than 0. Another important thing to remember about these designs, because these repeated measures designs are so powerful, if you got a big sample, it's going to be super sensitive. So just because you find a difference doesn't mean it's an important difference. It just means that sort of the difference is likely not 0, okay? Clinical folks looking at all of us, just because I found a treatment effect doesn't mean that's a useful treatment effect. It just means that something changed a little bit. That doesn't necessarily mean anybody's functioning any better than when we started. It just means that I started with a BDI score of 26 and now I've got a BDI score of 25. Yeah, it's not 0, but it's probably not useful, right? So this is where it starts to become important, sort of thinking about magnitude of the effects, looking at those confidence bounds and how much of a reduction should I expect from this intervention. Just given these intervention studies are almost always going to be paired sample designs. So again, with our tests, our question is do our difference scores across multiple assessments deviate sufficiently from 0 to assume that, like in the population, if I were to take everybody with PTSD and I measure them at one point and then give everybody the intervention. And then measure in the second point, does the sample that I've collected suggest that, give me enough evidence to suggest that there's probably some movement in those scores if I were to go through and do this. For our paired sample t-test, data is pretty straightforward, okay? We've got the mean difference minus the mean difference under the null. Amanda, what's the mean difference under the null? What's that?
The difference between.
Yeah, what's my assumed difference under the null? 0, yep. So this goes away. So I just end up with my mean difference over this over the standard error of my difference score. Okay. Standard error of my difference score, it's just the standard deviation of my difference score over the square root of my sample size, or the variance of my difference score over n, whole thing square root, however you want to go through and do it. Okay. And so this, my standard error here is my estimated standard error of difference scores resulting in sort of the expected difference in scores across repeated assessments, assuming the null hypothesis is true. Okay. So again, this is just a different standard error estimate. This is just the sampling. This represents my standard error of difference. Is just the standard deviation of the sampling distribution of my difference scores. So if I were to plot out for a given sample size, all possible different scores that could be generated from population error, from sample size, whatever, I'm going to plot those out. This is just the standard deviation of that sampling distribution. So again, we're taking the same stuff that we've always been doing. We're just kind of changing the units around a little bit. So the thing that we see in this small example here, let's say I've got 4 participants, just 4. Here's T1, here's T2. Okay. What I'm going to do is I'm just going to take the difference across these scores. Again, generally when you're doing this, take T1, subtract T2, and if you do that, that'll give you sort of the valence of that difference score is going to tell you whether it's increasing or decreasing. You can flip it around, makes no difference. It's just your sign's not going to match up with movement. That's fine as long as you understand that and interpret it correctly. But what we're going to see here is we go through and we calculate a difference score. And then all we're going to do is going to take the mean of that difference score, the standard deviation of that difference score, and that's what we're going to go through and plug up into our stuff. That makes some sense? Okay, cool. And the thing is with these types of what makes these so incredibly powerful, right? Let's say I've got 4, 5, right? And let's say I've got data that's 10, 53, 21, 7, and 98, right? And then here I've got 15, 57, 27, 13, and 100. Okay. How much variability do I have in that set of scores? A massive amount, right? And how much variability do I have in that set of scores? A massive amount, right? If I was running this in an independent sample t-test, is there any way I would get any sort of effect with that? No, they're all over the place, right? But in a paired sample test, that's +5, that's +4, +6, +6, +2. How's the variability in that set of scores? That's minimal, right? And so what we've got here when we're using this, and this is the part of the power of these repeated measures tests, is everybody's acting as their own control. So whatever makes Sam different from Katie, different than Basha, different than Elizabeth, different than Josiah, that's all getting partialed out, because what we're seeing, no matter where you start, we're still getting about the same level of movement forward across all people, right? And so what we're doing, we're cutting out all that garbage and noise, and all of a sudden we've got something that looks like a very systematic effect, even in this small sample. Okay. Other thing too, We go through, so looking at here, this is our difference scores. What's the probability of obtaining a set of difference scores with a mean difference of 3.5, assuming that null is true? The null assumes a mean difference score of equal to 0, right? So what we're doing is we're working with these difference scores. Okay? We go through and take at our formula for our paired sample test, right? What is this? Where do we see this formula? What is that a formula for? Yeah, you're right on. It's a single sample t-test. Matt, what is then this paired sample t-test? Yeah, it's the same thing. Paired sample t-test is just a single sample test on this vector of difference scores. That's all it is, okay? And remember, with that single sample test, how many sources of error do we have in single sample tests? 1 or 2? Just 1, right? So remember when we did the independent sample test, we had to double up that standard error. Here, working with a single sample, just 1 sample, only we're looking just at a vector of difference scores. We only have 1 sample, only 1 source of error. Everybody acts as their control. What ends up happening, we have a very, very powerful test that ends up with a lot more chance of identifying sort of the type of thing that we're looking for than if we were to go through and do our independent groups where we got, okay, this one group gets this manipulation, this other group gets the other manipulation. Okay. So just statistically, conceptually, this is where the power of these tests are coming from. Okay. Questions on this? So again, just remember this. Paired sample t-test is just a single sample t of the difference scores where my reference value is 0. That's all it is. And you can play around with this in SPSS. When we go through the stuff, SPSS will say, okay, here you go, you change this and that, sort of get things going on. Just for the hey-ho heck of it, just go through and calculate a vector of difference scores and just run an independent sample or a single sample t on those difference scores. You'll get the exact same thing as you got from your paired sample test. All right. Assumptions of our paired sample t-test. We're assuming our outcome is continuous, and we're assuming that the sampling distribution of different scores in the population is normal. Okay. So the trick here when we're screening our paired sample test, Sam, do we care about the distribution of scores at time 1? We care about the distribution of scores at time 2. We only care about the distribution of sample of scores in the middle. And so what we could end up with is time 1, time 2, that distribution of scores is way all over the place. Doesn't matter. We don't care. All we're concerned about is the different scores, right? So when we're going through and running our screening, first thing we'll want to do is go through and calculate those different scores, and then go through and run our screening on those, because that's what we're actually interested in looking at in our data. Okay. So again, sampling distribution of the different scores in the population is normal, and we're also assuming that our data doesn't contain extreme value stuff that's going to start dragging our image all over the place. Okay. And then all of our auxiliary hypotheses, right? Again, there's nothing we can do about this stuff. Most of these will almost always be violated. But I always just want you to keep in mind, like, okay, yeah, here's a system that works pretty good, but these are all the things that I have to watch out. Effect sizes for my paired sample t-test. Again, the mean of the difference score, right? I started here, I went to here. Again, for clinical folks, right? If I use a PCL all the time, or a BDI all the time, or an eating measure all the time, so I know what a big jump is or not a big jump is. That raw difference can often sort of convey quite a bit of meaning. Or if I'm looking at anything with a natural metric, sort of that raw difference can sort of start to give me information on how much of a magnitude thing is going on. We can also calculate Cohen's d. Again, we've got the mean of the difference score over some variance estimate. Problem is which one do we use, right? And again, we have some different options. Cohen's d, what we can go through is we can sort of say, okay, we can take a mean of the difference score divided by the average or the square root of the average variances. Okay, now again, remember that the square root of the average variances is not going to be equal to the average standard deviation, right? So if I take variance 1, variance 2, and variance at time 1, variance at time 2, divide that by 2, and then take the square root of that, I'm going to get a different number than if I just take the standard deviation at time 1, the standard deviation at time 2, take the average of that. They're going to be different scores, right? Remember that what we need to do is take the average of the variances and then take a square root of that. Do we need to pool here? No, why not, Amanda?
If they were different,
If my sample size at time 1 and time 2 are different, it means I have missing data and I can't use those people anyway. So by definition, with these tests, I'm always going to have the same number of people at time 1 and time 2. So I can just take the average. I don't have to fool around with pooling anything. Okay. So I can do this. I can go through and I can classes delta. This is all for a paired sample test. A lot of times our paired sample is like, okay, here we are at baseline, and then we implement some treatment, some manipulation, something like that. So oftentimes with our paired sample test, we have some kind of existing baseline that kind of makes sense. And so our glasses delta can be a nice option here. Okay. Then here, this is just a computational. We can sort of get it on R squared from our T statistic. This is just something we should for stuff. Don't worry about this too much. It's just sort of a metric that you can use. And basically, we're saying what percentage variability in our outcome measure or a time 2 is accounted for by our first time score, kind of like a regression coefficient type of thing. But for our purposes, this is probably where we're going to be living. A couple other metrics, though, to be aware of. We could calculate an effect size taking the mean of the difference over the standard deviation difference scores. Okay. If I'm going to calculate a confidence interval around my effect size for this is what I probably need to use, because this estimate here is going into the and is what's being used to calculate my test statistic. And for reasons we'll get into, that starts to become important in getting proper confidence bounds around this. Issue is, if I go through and I'm trying to report a metric that's interpretable, right? And I'm using the standard deviation, my difference score as my standardizer, okay? Think about here. Let's say I go through in this test and I calculate glasses D, where I'm using the variability of my baseline scores as my standardizer, okay? Think about that value versus if I use the standard deviation of my difference scores. What's going to happen if I use standard deviation of my difference scores as my standardizer? What's that going to do to my effect size? Yeah, it's going to make it blow up through the roof, right? Variability in my difference scores is quite small, which is kind of what I would hope, because I'm seeing a systematic impact of my intervention. Variability at baseline is all over the place, right? And so what'll happen is if I use this as my standardizer, what can happen is that I can end up with a effect size that's much, much larger than what I would, the corresponding effect size that I would report for, say, an independent sample test, right? So I might find that I have actually quite a small effect size based up, I'm looking at standard deviation unit difference relative to baseline where everybody started out, versus this weird sort of kind of circular logic in terms of thinking about the standard deviation unit difference in standard deviation difference, which starts to sort of make my head spin in terms of stuff. So there are times when we're going to use this, namely if I want to calculate a confidence interval around effect size. But what I need to do is sort of double check, and sometimes they're comparable. But what I want to do is go through, and if this is way more than what I would expect, sort of given some of these other metrics, want to be careful about that. Other thing is we see we have an effect size with a repeated measures correction. Basically, I'm calculating this cone using the square root of my average variance, and then I'm dividing that by a correction factor, looking at the correlation between my time stuff. This starts to become important for power, but again, is something that one starts to erode in terms of my actual practical interpretation of what that number means, and then also something that starts to inflate sort of what that number is, which is tempting because it's always nice to say, hey, look at the massive effect size that I've got. We already have a problem of overestimating effect size in the literature. We got to be careful that we're trying to put in real estimates of stuff. So this is a thing that you'll probably see more often than not. Just note that sort of there are some issues with sort of what's likely to happen if you use this as your measure of effect. Important for power, essential for calculating power, but in terms of an interpretable effect size, we start to get into some problems. All right, so let's go through and jump into this SPSS example of anger imagery. What we've got here is we're saying researchers interested in the impact of mental imagery on the regulation of subjective anger. So we do a pilot study to determine if the efficacy of an experimental manipulation that we hope to use for a different project, right? So what we do is bring people in, get 0 to 10 baseline ratings of anger, 0 no anger, 10 extreme anger. And then we have participants imagine a time when they experience intense feelings of anger. Participants complete a 2-minute period of negative imagery before rating peak levels of anger experienced during the manipulation. So we do that, get a baseline measure, have them do this for 2 minutes and then say, okay, how high was your anger at its peak when you were going through and thinking about this, okay? Participants are then told to stop thinking about the anger memory, instructed to instead imagine a time when they experience intense positive emotions. Following a 20-second delay, participants are instructed to rate current levels of anger every 20 seconds over a period of 2 minutes. Increases in ratings from baseline to peak anger during negative imagery, and reductions in subjective anger from the first to the final rating during the positive imagery proposes evidence of successful manipulation. Okay, so what we're doing is have people come in, get a baseline. For 2 minutes, have them think about something that really ticks them off, and then rate the peak anger that they felt during that. Then we want to try and reverse that, right? We say, okay, what do we want you to do now? Think about something positive. And every 20 seconds, I'm going to ask you to go through and sort of give me a rating of how angry you are right now. I'm going to do that for 2 minutes, and by the time we get to the end, you're going to have an end rating there. Okay, so going to go down through sort of null, alternative, confidence intervals, all of that business. For the sake of time, paired sample stuff here in terms of your screening, these data are looking pretty good. The only tricky thing here is you first have to calculate a difference score in order to go through, and that's what we're working on the screening. I've got a video sort of up on the YouTube channel that sort of kind of walks through that screening thing. I'm gonna let you go through and watch that. It's pretty easy, straightforward. What I want to do is just get to the analysis so we can walk through sort of that piece of things here. Okay, so if I'm going to go through, pull up our paired sample stuff here, and the cases that I'm interested in, or the variables I'm interested in looking at, are my anger start. So this is my baseline. So I'm going to go through and sort these. That's looking pretty good, right? And my anger peak, that's my first test. We go through and sort that. Those are looking good, okay? And then my sub anger, I'm gonna sort this. See, I'm missing someone with a value here. And so that's my first anger rating, my second anger rating, sort of missing that same one there. So we'd go through and say, okay, participant number 18, missing those, right? So I'm going to go through, clear that out. And so now I have my full set here. Okay. So what we're going to do in this screening video, again, it's pretty straightforward. There's nothing really too scary going on in these data. Everything kind of falls into line. Basically, in SPSS, you're just calculating a different score and then running your distributions, your z-scores and stuff like that on that. Pretty straightforward. Okay. So we're going to say we've gone through and done that. What we want to do now is go to analyze and go down to compare means and go to our paired sample t-test. Okay. And what we're going to do now is we're just going to start dropping things into the box to go through and just run our tests here. Okay. So we're going to go, remember that for these, in order for the valence of your point estimates to match kind of if it's going up or down, want to take your last estimate. subtract it from your first estimate so that everything makes sense in direction. You don't have to, it's just easier. So I'm going to take peak anger, because that's my sort of second point. Take that and then subtract it from my first. And so we can see up there what SPSS has done is it's saying variable 1, variable 2. It's got my anger matching scores across there. Okay. Then I'm going to take my last anger rating during my positive imagery. I'm going to drop that here. Take my first anger imagery rating, drop that there. There we've got things going on, okay? The only other thing, so we've got estimate effect size, but here we've got some different metrics that we could go through and run. We've got standard deviation of the different scores. That was the one I said we have to be careful because that can inflate our estimates. So we're not going to choose that one. So we've got corrected standard deviation of the difference. That's basically a Hedges correction on sort of the one metric that I am worried about. Average of variances, that's that Cohen's d that I want. So basically you're taking the square root of the average variance. We're going to go through and request that for this group. Okay. You go ahead and hit paste. I'll just go ahead and hit OK. And here we have our output. Okay. So again, always when you're running tests, go through and take a look at this descriptive table to make sure that you've got the people who you think you need to have in here. Okay. Looks all good. Sort of 42 people. Sort of peak anger, initial recovery, initial recovery, make sure the variables are sort of you're preparing the same things that you intend to here. Here's our paired sample correlations. Remember when I told you that one effect size where you're going through and correcting based on the correlation between your two measures. That's kind of what this is looking at. So it's telling you this is interesting information. To what extent do scores at time 1 and time 2 correlate with one another? Here, it looks like my peak anger and my initial anger are quite a bit different than my recovery 6 and my recovery 1. Kind of makes sense, right? Because that first time I just had people coming in at baseline and then having them image versus like the second time everybody's kind of on the same spot. So that kind of makes some sense. Then we have my paired sample test. Okay. So here is the mean difference for peak to initial and recovery 6 to recovery 1. For the first thing, right? So we're seeing increases in peak anger, right? So that's awesome. Again, remember this is a pilot test. So I want to see increases in anger if I'm having people think about angry stuff. So it looks like we're getting increases from recovery 6 to recovery 1. If we're having people think about positive stuff, changes in anger, we're getting it in the right direction, but sort of much more modest recovery with that. Okay. So this is my difference score. Here's my standard deviation of the difference score. That's this, right? Remember, that's the value that's going into the calculation of my standard error for my test. Here's the standard error of my difference. Here's the confidence intervals, right? For my the difference or the change in anger during the anger activation test. And here's the confidence intervals for my reduction, my t-tests, degrees of freedom, and my two-sided tests. Okay. So Emily, what am I sort of seeing based on sort of these estimates here? What's that? Our manipulation is having an effect. Yeah, right. So we do have evidence based on the data we've collected that in our anger, our anger manipulation, where we're asking people to sort of think about stuff, we're seeing sort of non-zero increases in anger ratings, specifically anywhere from an increase in anger rating from about 3.8 to a little over 5 in terms of increase. So that's pretty impressive. Anger reduction, maybe a little more modest. So anywhere from about a 1 point increase to a 5 point or 1 point decrease to a 5 point decrease in terms of, about a 2 point, anywhere from a 1 point to a 2 point decrease for sort of the positive imagery stuff. Okay. But this is good, right? We have, based on the data, we say it's essentially not doing nothing, right? So that's pretty good. And it's doing things in the direction that we'd expected. Also good. If we go down through and we take a look at our confidence bounds, right? We see here, we've got samples of 40, so I'm probably not going to worry about Hedges correction really here. I'm looking, I've got, boy, we're seeing an increase in anger ratings from that anger rumination. We're getting, working close to 2.5 standard deviation increase in anger ratings. That's super powerful, right? Now, in terms of the anger reduction, got about 0.7 of a standard deviation reduction in terms of our point estimate, which is still something, right? But it's not as, it's not as, which of these looks to be sort of the more effective or sort of the more powerful intervention? Having people think about really angry stuff or having people think about sort of positive stuff to reduce anger?
The angry stuff.
Yeah, right. And again, it's both 2 minutes, right? But 2 minutes of like, once I've got you already cranked up, having you think about positive things maybe is not as effective in reducing anger. It's not doing anything, but it's maybe less powerful than having you sit there and ruminate about something that's really got you upset. Okay. So paired sample test, pretty easy and straightforward. Anybody have questions about so what we saw in that output? Okay. So here's just a test, sort of going through doing stuff in SPSS. Here's our output. And then again, our write-up. Again, this middle piece, this is all screening stuff. Take a look at it, sort of read through it, kind of see how, anytime you're exposed to language on how you might talk about things is kind of nice. Like sort of my entire graduate training was trying to make my stuff sound like something someone's who is smarter than mine with published things. It's a good way to kind of make it until you make it. So go through and kind of take a look at that. That wasn't to say that I'm smarter than you. I'm not. You guys are brilliant. It's just that I've been working at this longer for a way to sort of put things together. Okay. But sort of going down through and taking a look here, say scores collected in the pilot study provides strong evidence against models specifying zero difference in ratings of anger during negative and positive imagery, right? And so here we're just dropping in our stuff, right? Just, we don't have to say that it's significant or anything like that. We just say, hey, we got a lot of evidence that this is working out, right? The 4.5 unit increase in subjective anger following negative imagery task, consistent with the 2 2/3 standard deviation increase in ratings relative to variability at baseline. What I did here is I went through and I just calculated glasses delta, because I've got a good baseline. So I like that as the standardizer for that. Data are compatible with increases in anger ranging from 3.8 to 5.1 units in a hypothetical population of completing the manipulation. Okay, the only people, these are the 40 people, or maybe the only people who've actually completed this. So like the population, that is the population, right? But that's not what we're interested in. We're just thinking about hypothetically, if we brought all the people in the universe in and did this, how much of a change would we expect? Well, somewhere probably based on these data from 3.8 to 5.11. Right? It's important to note that the lower bound estimate provided by this interval continues to suggest over a 2 standard deviation increase in anger ratings relative to variability at baseline. So even the low end suggests that we're getting a huge increase. Point estimate of anger recovery in the positive imagery was more modest, but continued to be consistent with the conventional benchmarks for a medium-sized effect. So Amanda here, I'm kind of working that and I'm saying still good. So the conventional with medium-sized effects, right? 95% confidence interval indicated identified anger reductions ranging from 0.96 to 2.2 to be plausible estimates of change in the larger population. Results provide support for clear and observable change in subjective anger following both manipulations, although anger imagery appears to have a stronger influence on subjective experience than its positive imagery. Okay. I'm just kind of taking that, pulling it all together to say, okay, what are we asking? What can I say about it? As opposed to we have significant differences in anger, significant changes and stuff, which tells me very little to nothing about sort of which way that's gone, sort of what types of change should we expect, right? So for you experimental folks, like I would much rather have something like this, because then I'm saying, okay, yeah, this is, if I were to implement a study with this is kind of about what we found in this study, but really anything along these from here to here, if I were to do this, this is kind of what I should expect. So I might even, if I want to be conservative, take the lower end estimate and say, okay, minimum, this is kind of what I would expect based on these data to find out. And that way, if it's higher, then you're kind of pleasantly surprised, but sort of using that to try and gauge. So what would I expect to see in my folks? Same thing, clinical folks, like, okay, here's an intervention. And we're seeing from pre to post test in terms of symptom measures, we're saying this is how much of an average reduction we saw, but really data would support anything from this to that. That's really powerful. That's saying, hey, if I were to run this intervention, I would expect on average my clients to drop from anywhere from here to here, right? And depending on how wide that interval estimate is, really, really big impact on how confident I am on sort of the extent to which this is going to be potentially useful. So just thinking about practical impacts of stuff. This is just how we might go through and put it together for a write-up for publications. So I want to finish up here with strengths and limitations of our paired sample tests. Again, incorporating phenomena that we are often interested in looking at within the context of psychology, right? Again, an efficient use of resources and this reduction in error variance that we see for all the reasons that we talked about. These are very, very, very powerful analyses. This is Zach Williamson, who's now a professor at the Community College in Wyoming, that repeated measures are pretty damn slick. This is the photo he provided of himself, so he's looking sharp there. But they are pretty damn slick. And when we think about thesis, projects, dissertations, and stuff like that, anything that you can reasonably incorporate or repeated measures into, you should, because it's a much more powerful test, and you've got a much more likely, a much better likelihood of finding what it is that you're trying to find. But we do have limitations here, okay? Time-related factors. If I'm measuring at time 1 and time 2, and there could be something that's going on in between time 1 and time 2 that starts to impact sort of the thing that I'm trying to measure, we need to start thinking about that. Sometimes that's sort of talk about that as effective maturation or things like that. If we got to have confounders in there, we need to think about that a little bit, right? So if you want to see, Christina, the impact on of some intervention on kids stuff, or Teresa, some intervention of some kids stuff from 5th grade to 3rd grade, and you say, oh yeah, that's my intervention worked because they got an increase in socialization, emotion regulation, so general verbal ability or something like that. Like, well, yeah, no joke, because you measure comparing them in 5th grade, like of course that's going to increase, right? So needing to think about that. Influence of practice effects. Sometimes we're asking people to do things that once you've done it once, now you know that, then the game's up, and I can't ask you to do it again because you already know the answer, and so that kind of fools with stuff. Order effects, right? So maybe if I go through and I get you really mad and then try and make you happy, then that's going to be a hard thing to pull off. If I make you kind of happy and then make you upset. We've got some counterbalancing stuff that goes on with this, but same thing if I'm running a clinical study and I say, okay, I'm going to teach you CBT stuff, and then I'm going to do some other thing. I'm like, oh, hey, forget about all the therapy that we did before and only do this. That's not a reasonable thing, right? So it's really hard to do within subjects or within person's tests of those types of things. And so sometimes this is just out of the picture. But if there is a way to go through and put this in, counterbalancing is a nice tool to try and address maybe some order effects, so long as those carryover effects don't spoil sort of later observations completely. This is a good approach to take. Okay, so just to finish it off, we've got our single sample test. This is where we're with a single sample test. We're comparing the mean of some continuous variable from a single sample to some known population reference mean when I don't know the population variance. If I know the population variance, what can I use? What's that? Yep. And so what test is that? Is it a T? What? It's a Z. Yep. If I know the population variance, then I'm rolling with Z scores, right? And that's cool. Rarely have this situation. So generally what we're doing is I'm comparing my sample from my population against some reference value. using my sample variance. So again, testing our hypotheses that the population from which the sample was drawn has a mean equal to some value of interest or some reference population. Independent sample T, here I'm comparing means of continuous outcome variable on two independent samples, right? And we're testing sort of whether or not these two samples are equal, coming from populations with equal means, right? On our current sample test, again, continuous outcome, collecting measure on two occasions, looking at different scores. Again, the asterisk there being that sometimes if we have a matched pair design, we can still use this so long as we just have to say person A corresponds to person A, and the control person B, so on and so forth. And again, testing the null that the mean of the different scores in the population is zero. All right. Wow. I've never done this before. We've never been at this point in time on target with stuff ever in the history. Like what I've been teaching this for, yeah, 9 years. Like never has this happened before where we're actually on target to be sort of moving forward with things. So you all are fantastic. Thank you. So we kind of did a little bit of a rush through that last piece. I'll go through and send you links to a playlist with a bunch of different stuff in there. What you can do is there's a example of me working through the screening of the paired sample tests, just so you can go through and watch that and get on track with that. But you all are ready to rock and roll with stuff. So nice work. Okay, awesome. So problem set 4 will be due not this coming Friday, but next Friday. And then we'll have next week, we'll talk about confidence intervals around effect size and some power related stuff. And then we'll roll the following week into the in-person midterm. So don't worry about in-person midterm right now. So worry about the problem set. But if you ignore that and want to worry about the sort of midterm, I'll turn the rest of you loose, but if you have questions, so just come up and ask me. All right. Thanks, folks. CJ, this is a big day. This is a big day. Never has this happened before.